Hello. Might be wrong, but I think Geraldine, Grant, and Paul and Parker. So everybody except for Chase. I need to see for portfolios. Wait, hold on. This is B-Day. This is B-Day. Parker, we didn't meet last time, did we? No. Grant, did we meet last time? I don't think so. Geraldine, we didn't meet last time either. So yeah, I was right. Okay. Even though you guys are B-Day, which meant you weren't supposed to see me Wednesday normally, because you didn't see me last time when you had to, I needed to see you. So everybody except for Chase, can I see you guys sometime after school today, or is that not going to work? Yeah? Will that work? Okay. Here's the problem with that. Because I'll be able to see you after 2:35, and I'm only supposed to be here until 3:30. Plus, lots of people did not meet with me when they were supposed to. Something sophomore class. It's going to be kind of crazy. There's going to be a bunch of people trying to get in. There's no official schedule for it, so it's going to be a first come, first served type of deal. Which means you might show up right at 2:35 online, and I'll have to say, sorry, I'm with someone right now. You're the 5th person in line. As soon as you see this person come in and go out, then you'll be the next person into the Google Meet. It could be like 10 people. I don't know. But we need to get this done. I apologize that there's no schedule and that it's so many people doing this, but it's not much I can do about it when I gave you guys all Wednesday to get it done, right? And I know some of you guys had really great excuses or whatever, and that's fine. I assume everybody has a good excuse. I don't, it doesn't matter to me. But that's why I give you guys Wednesday, so we can avoid stuff like this. I can't be doing makeups like this going forward. I'm just doing it this one time because I want to make sure you guys are caught up. After that, I can only devote an entire day out of the week. I can't be staying until like 5 o'clock on a Friday because you guys couldn't be bothered to show up during when I'm getting paid. I got stuff to do, like stuff I have to do, unfortunately. But I do want to make sure you guys get caught up. Remember, for this one, since you guys are B-Day people, I don't need to see any of the stuff I had on the board earlier in the week, those 3 things. All I need to see is
I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. Every day I make sure.
All I need to see is an example of addition, subtraction, or multiplication problem that you've chosen to explain. And again, don't just be like, oh yeah, I add these 2 numbers and I carry the 1. Explain why you're carrying the 1, what that represents, how it's thinking about the problem. Make sure you show clearly that, look, even though I'm thinking about the problem like this, it's literally the same problem. For instance, if I was doing 35 plus 55, not a great example, but a decent example, you might say, well, I've got 30 plus 5 plus 50 plus 5. And the reason that's okay is because 30 plus 5 is just 35, 50 plus 5 is just 55. It's not looking at it, it's not changing the problem, it's just looking at it a different way. But it's easier to do because I've got 30 and 50, which obviously is 80, and 5 and 5, which is obviously 10, so the answer is obviously 90, right? I don't need lots of ways of explaining it. I just need at least one good way of explaining it. And then I need you to have done some kind of, any of the problems that I posted on Google Classroom to attempt that and explain your reasoning behind it. That's all I need to see. And then for next week, I'll need the 3 things on the board plus what we're doing today. What's up, Joe? Hey, Afton. All right, so let's get attendance done. Let's get into this. I want to review what we did yesterday real quick and then jump into what we're doing today. All righty. So yeah, if any of you did not meet with me, because everybody at home is an A-Day person, if you did not meet with me on Wednesday, for whatever reason, I need to meet with you today, as soon as possible, after school, starting at 2:35. I'll send out a Google Meet link for that. All right, so I see Joe and I see Afton. I see Carly. no Connor, Blaze, Jocelyn, or Brennan yet. Let me know if you're here. Meantime, I want to review what we did yesterday. Oh, we have those people coming in. So we said yesterday that Euclid has 5 postulates. The first 4 are kind of boring and self-explanatory. Something, something, something. Segment addition postulate, right? You have 2 segments. You can put them together and it'll make a whole segment. No big deal. Any 2 points will make a line, right? No way to prove that, but that's always true. So we kind of skip over those. But then you get to the 5th postulate, the last postulate. His whole idea of mathematics is just based on 5 leaps of faith. Everything else we can prove. It's pretty good, actually. But the last postulate is the parallel line postulate. And basically it says that if you have 2 lines and a third line that cuts them, we call that line the transversal. I'll write that out. That's why I usually use T for this line. A transversal is any line that cuts 2 others. So that's a transversal. If that transversal makes 2 interior angles that are on the same side of that transversal, we call those same side interior angles. Grab a bright green. So these are same side of the transversal, right? They're both on the right side of the transversal, and they're inside the parallel lines. If those 2 angles right there, if they add up to 180, then these 2 lines will never touch. In other words, they're going to be parallel, right? We got train tracks going on here. So basically he's saying if this is true, then L is parallel to M. And again, this is a postulate, so there's no way to prove that. But that's how we went about it. And the reason for that is because you can imagine having a straight line right here, one that's 90 and 90, right? They add up to 180 total. And if that distance is the same as the distance between here and here, then those lines must not be getting any closer to each other. And if they're not getting closer to each other, well, then they're never going to intersect, right? That's the idea. Euclid expanded that out saying, look, I don't just have to go straight up to make sure this measurement's the same. I could do this and have the same angles there, right, as the green and the blue, and I could measure that amount, and that'd be fine. If we're measuring our heights, we can stand back to back, and that's a really easy way to do it because we're both standing up straight, 90 degrees, right? But we can also both lean the same amount, and we'll be able to tell whether they're the same height or not. As long as we lean the same amount. If we don't lean the same amount, well then, I have one hand that looks like it's a lot bigger than the other, right? So he says as long as they add up to 180, leaning the same amount, you can measure accurately. And when you measure accurately and show that the lines aren't intersecting, well then they never will. So that's his postulate. Again, it's a postulate. It's a leap of faith that we have to take to be able to do anything more in math. And the reason we take those as mathematicians is not because, well, you know, we're scientists and but sometimes we just have to take a leap of faith. No, it's because we're mathematicians and it's more interesting if we take that leap of faith. And mathematicians are always about going after what's more interesting. Not being able to do anything because, oh, you can't tell, right? Leads to a very boring and non-interesting world. So we take this leap of faith because how else could it be? And we explore it. In fact, there's an alternative to taking this leap of faith called non-Euclidean geometry, where they say, you know what? What if this isn't true? What if you could measure the same distance here and here, but eventually they do end up intersecting? Seems kind of weird, but we can't prove it has to be that way, so what if it isn't? And they call that non-Euclidean geometry. And actually, non-Euclidean geometry sometimes describes our world better than regular geometry. As weird as that would be for 2 parallel lines to eventually intersect. Turns out space-time is curved. What do I mean by that? So imagine a trampoline, right? And you got this really heavy bowling ball or something on one spot, so it dips in, right? It dips in. Now, across from that bowling ball, you put a little golf ball, right? What's going to happen to that golf ball as the trampoline dips in from the heavy one? It's going to roll towards it, right? So Einstein theorized that this is how gravity works. Gravity is space-time, but with a heavy object kind of pulling it down, like a planet or something, and then smaller objects go towards it. That's what's going on. Heaviness, mass, actually bends the fabric of space, or the trampoline. But it turns out space is curved, especially around big, massive objects. So going straight, even though it appears straight to us, might not actually be. A good example of this, in our feeble little minds, is to take a globe and draw 2 quote-unquote straight lines on them. I don't know if you guys can see that or not. There's 2 straight lines on there, but the thing is, we know the globe is curved, right? So those straight lines actually bend backwards, yeah? So what appears straight on a curved surface is actually curved. And what I draw curved on here might actually be straight when we map it all out. So, like, if you were to take, if this was a globe and had a map on it, right? I could peel that map off and then lay it flat. And if I were to lay it flat, it actually wouldn't be able to be laid perfectly flat. It's impossible. There's actually a proof behind that. I'll show you someday. And when I lay that flat, what once was straight, like the lines on a globe, will actually curve when we flatten it out. So what is straight is curved, and what is curved is straight if the world is round. And it turns out the universe is. So it's always good to remember that this version of geometry, well, it seems like, you know, oh, that's how the real world works. It really doesn't when you get to, you know, large scale or really tiny scale, right? Atoms and electrons, or big scale like planets. But we use it anyway because it's a very good approximation. And for most things that we do, like building bridges and all that stuff, this stuff holds up pretty true. These lines will never intersect. And on and on and on. Anyway, so we're going to deal with Euclidean geometry. Euclid was a guy in ancient Greek society. Pretty successful mathematician. In fact, I almost named my cat Euclid. But I chose other mathematicians. Alright, so transversal, any line that cuts two other lines. If that transversal creates two same side interior angles that add up to 180, in other words, supplementary angles, right? We call this being supplementary. Got tired of saying they add up to 80 so much, so they just invented a word for it. Then we know lines are parallel. This works both ways. So if we think of this as proposition A, and we think of this as proposition B, it turns out that A always gets you B. So if we have these angles adding up to 180, then we know automatically these are parallel. That's what I said earlier, right? But we also know the other way around. That if we have two parallel lines, whenever I draw a transversal, the angles right here will always add up to 180. It goes both ways. We're supportive of that in here. Doesn't always happen that way. I used the example yesterday that proposition A could be you play dumb games. Proposition B would be what? What happens when you play dumb games? You win dumb prizes. You heard that one? So proposition A, you play dumb games. Proposition B, you get dumb prizes, right? One drives the bus. If you do A, you get B. But in this case, the opposite isn't always true. If I flip those two ideas, you play dumb games, you get dumb prizes, and I switch it to, if you got dumb prizes, then you must have been playing dumb games. That's not always true. Some people get dumb prizes without playing dumb games. That's life. So not always does it go both ways, but when it does, it's super useful. So we're going to talk about that today. And all the different ideas that this implies. We're first going to start here. And I'm going to tell you these two lines are parallel. I'm going to draw a little arrow that's colored in. And that shows you that they are. So we know that L is parallel to M. And I'm going to drop me a little transversal. We'll call it T, because why not? I'm going to number these angles real quick. We're going to talk about what these angles are and what properties they have. Because parallel lines are really nice. Because when we have them being parallel, we get a lot more information for free. This is going to be super useful later on in geometry. Because we're going to have all these crazy diagrams. We're going to have to prove this crazy awful idea. And we're going to be like, I don't even know where to start. Well, if you have parallel lines, you get a lot of free information. And even though that information may not be helpful, it's still true. And it could be helpful, right? So, we've got 8 different angles here. Because Maddie isn't in this class, but Maddie's favorite number is 8. That's why there's 8. So, what do we know about these angles? First of all, I'll ask a question that I already gave the answer to. What do we know about angle 4 and angle 6? What must be true according to Euclid's Fifth Postulate? Yeah. They're supplementary, exactly. So we know for sure. I'm going to do a little therefore symbol, kind of get you guys in the mood of using this symbol, because it's, I don't know, it's kind of badass. Therefore, we have this, therefore, angle 4 and angle 6 are supplementary. Cool. Now I told you we get a lot of information just from this, right? That's the postulate. But there's a lot more we can get from that actually, using our other theorems or postulates to figure out more about the relationship between these angles. What do you know about the other angles? Remember, whenever you say you know something, try to explain why. If you can't, that's okay. Maybe someone else can explain for you, right? Hey, Connor. Hey, Blaze. Anybody else here that I need to mark present? We got a Jocelyn in the house, a Brennan. Massandra is absent, it looks like. What else do you know about these angles? Parker, give a shot. 3 and 5 are what? Supplementary, yeah. I mean, we chose the right side, same side angles. Why couldn't you choose the left side? So these two are supplementary. Now, I use color often to denote which angles are congruent, meaning the same. So just saying they're supplementary doesn't mean they have anything to do with this off the bat, right? However, before I mark these down, there is a connection between 3 and 5 and 4 and 6. I know these add up to 180, but I also know they're congruent to these angles. Which one goes with which, you think? 3 and 6? He's right. How do we know that? This is what we've known so far. We know that 4 and 6 are supplementary. How do I know that 3 is green? Supplementary means these two add up to 180. So blue and green add up to 180. If you have blue, green's the only one that's going to add up to 180 with it. So if blue is like 40, this would have to be 140, right? Has to be. There's no other number that adds with 40 to be 180, right? So if this is 40, how do we know what 3 is? How do we know 3 is also 140? What do you notice about angles 3 and 4? Ooh, yeah, he's doing this. We're doing the miming thing. I love geometry class. It's the only class where the answers are most often given with signals, right? They do this. It's like this. What does he mean by this, Chase? He's talking about angle 3 and angle 4. Can angles be parallel? No, that's not what he means. Shame on you for not understanding this symbol. It's international. It's so clear. 3 and 4. Parker's not allowed to tell. Okay. Playing charades. Four words. What about 3 and 4 is this? Paul, you back there Googling what this means? Good idea. Somebody's got to get on it. What do you think he means by this? About 3 and 4. We know 4, if it's 140 degrees, this has to be 40, right? Because they're supplementary. Only way to make 180 if this is 140 is to add 40 onto it, right? I'm just throwing out numbers. If this is 140, how do we know that this is also 40? What does that have to do with this? Nobody? Oh man, Parker, you're gonna have to tell him. So when he's saying this, he's talking about line L. Do you see how both these angles make up line L? Like here's the big angle, right? I won't draw it in, but like the angle here is definitely 180. How do we know that? Because that's a straight angle, right? It's a straight line. Any line, let me draw it up here, is 180 degrees. And we know that from here to here. Because if we were to do the bottom half of it, doesn't it make a full circle? And doesn't it cut that circle in half? Oh, whoops. Hey, Brennan. And we know a full circle is 360. How do we know a full circle is 360? Call of Duty, right? 360 no scope, right? Come on, we know. Aim assist. Anybody can do it. Snoop Dogg 420. All right, so if the whole thing's 360, then half of it has to be 180. So a straight angle is 180. And this is a straight angle because it's a straight line, right? So we know whatever 3 and 4 are have to add up to 180. Well, if blue and green makes 180, blue and red can't make 180 because red would have to be a different number, right? This has to be the same number as this. Otherwise, we wouldn't have 180. If this is 140, this is automatically 40. If this is 140, that makes this guy automatically 42. See how those will have to match? We call this linear pair theorem. By linear pair theorem, we know that 3 and 4 have to be 180 in total. They have to be. Because they're a linear pair. Linear meaning line, right? Pair meaning two. Two angles making up a line have to be 180. That's linear pair theorem. So we know that angle 4 plus, I'll use angle 3 in black, must equal 180. Well, if angle 4 and angle 3 equals 180, and angle 4 and angle 6 equals 180, doesn't this equal that? So I can write this out. I'm showing it very mathematically. Therefore, angle 4, use a little therefore symbol, angle 4 plus angle 6 should equal angle 4 plus angle 3. Therefore, we use a lot of therefore when we're just doing algebra, right? This is 180, that's 180. We can switch those out, right? So instead of this equals 180, I can switch out 180 for this. You can say that's by substitution. SUBS, substitution. We switch those out. You guys know what substitute means? Right, when I'm absent, they bring somebody into... And it has to be the same, right, when you substitute something, right? What do you want to drink? I'd like a Coke. Oh, sorry, sir, we only have Pepsi. Some people would say they aren't the same. That's not a viable substitute. Some people say, you know what, it doesn't matter. Cola, we're good to go. Some people would say when I'm absent and they bring in a substitute, it's basically the same thing, I mean, right? Can't even tell the difference sometimes. Other people say maybe not, right? You don't even know. I could be a sub right now. Dive, dive. Not that kind of sub. All right, so this is true because this equals 180, and 180 is the same thing as that, so this must equal that. I substituted. And then by algebra, if I subtract the same thing from both sides, it doesn't change the problem, right? It keeps it true. If I have 5 equals 5, that's a true thing, right? And I subtract 3 from both sides, now I have 2 equals 2. I'm not a crook. Still a true statement. It's a different statement than 5 equals 5, right? 2 equals 2 is different than 5 equals 5, but it's still a true statement. If I subtract angle 4 from both sides, I get a true statement. I get angle 6 is the same as angle 3. In other words, angle 3 is green, baby. I like them apples. That's what Parker was saying with this. I said it like that. I prefer this because then Chase can understand what I'm saying. But you know what, Parker, I understood. All right. So we've got same side angles here and same side interior angles here that are supplementary. Also, we have same side alternate, right? Opposite sides, see how they're an opposite? Those are congruent. So same side interior, they're going to be supplementary. Alternate interior angles, they're going to be congruent. In fact, we have that be a theorem because all this is pretty wordy to prove it every time, but we know it's true. That'll always be true. No matter what lines I draw, as long as they're parallel, alternate interior angles will be congruent. So we call that alternate interior angles theorem. So what we just proved was alternate interior angles theorem. Alternate meaning opposite sides, right? Interior meaning on the inside of the parallels. Alternate interior angles are always congruent. They're always the same. Very, very useful. Instead of having to write all this, you can cut to the chase, no pun intended, and just say those are congruent. Alternate interior angles theorem. If I ask you to prove it, that's how you do it. Well, I know these are supplementary, and if these add to 180, blue and green, and these add to 180, then I know this must be blue and green as well. Green and green, blue and blue. Alternate interior angles are true. They're congruent. What else do you know? We haven't talked about our exterior angles, have we? What else do we know about them? Parker, you raising your hand or you give me the high sign? Little rascals. 8 is equal to 5, 7 equal to 6. Parker's correct. How do we know 8 and 5 are the same? Somebody other than Parker. Yo, Chase. Couple ways, actually. Ooh, darn. I can think of 2 different ways. How do we know that 8 and 5 are both blue? Maybe Parker doesn't even know. He just feels it. Unfortunately, getting the right answer in here will not be enough to get, you know, a thumbs up from me. You have to be able to explain it as well. Knowing the answer is 5 has never been enough. We tricked you into thinking it was. How do I know that's true? You need to know this for next week on your portfolio. Yeah.
Vertical angles.
Vertical angles theorem, right? Vertical angles, the angles up and down, and any x will always be the same, right? If I take this x and I bend it, notice the top and bottom change the same way, don't they? They get smaller and bigger together. They're always going to be congruent. There's a way to prove that. It's very simple. I know red and green must be 180, right? They're supplementary. And I know this angle in green must be 180. Well, if this in green makes 180 and this in green makes 180, right? If this guy was 140, this guy'd have to be 40, right? Well, this guy's 140, this guy also has to be 40. So it turns out these will always be the same. We can do the same thing for the side angles. If this and this makes 140 and this makes 140, well, this and this should make 140 as well, right? So it turns out the side and the top and the bottom are always going to be the same. They call it vertical angles theorem because they focus on the top and bottom, but it's really horizontal angles theorem too. This works for any x. Another word for this is scissor theorem. Your word's not mine. I think Alexander's going to coin that term. Something about the angles. They're doing the scissor thing and they're the same, right? Your word's not mine. But you can call it scissor theorem if you want. So yeah, these are congruent by scissor theorem. Oops. Or vertical angles, because if you turn it, right? There's our verticals. Has nothing to do with them being parallel. It's just there's an x. So Parker also said 1 and 4 are the same. Vertical angles there. What's another reason that 5 and 8 have to be the same? We had this before. Why do 5 and 8 have to be the same? Give me another reason. Uh-oh. It's the feds. Oh no. Ronald himself. Where's my money? Ronald McDonald House doesn't pay for itself, Parker. Not a charity. What do you know about 5 and 6? They go 180 because they're on a straight line, yeah? What do you know about 6 and 8? 180 because they're on a straight line. So if you're telling me green always goes with blue to make a straight line, then green's always going to go with blue to make a straight line, yeah? Same crap we did here. So you can do it that way, or you can just go cut to the chase, vertical angles theorem, right? Because basically the way we did it here was kind of the proof I did for vertical angles, right? Theorems are nice because they let you cut through the proof and just say, hey, it is. We already proved that. But if you forget the theorem, prove it, right? Well, I know this is 180. And so if this adds up to 180, and I know this adds up to 180, then green and blue is always going to be green and blue for 180. What else do I know about these angles? Oh, hold on. It looks like 1 and 8 are the same. They're exterior angles. Are they same side exterior or alternate exterior? How would you describe them? Alternate, right? They're opposite sides of the transversal, right? Same side is like this. That's same side interior. Here's alternate interior. Same side, or I'm sorry, alternate exterior. This would be same side exterior right here. So what do you know about 2 and 7? Let's talk about those alternate interior angles here, or alternate exterior angles here. Well, if these alternate exterior angles are congruent, I bet these alternate exterior angles are congruent as well. Looks like that's a property of alternate exterior angles. How do I know 2 is the same as 3? Yo. Vertical angles. Give me another reason. How do I know that? This is what I had before. Somebody. Yeah, green and blue are a linear pair, right? So if I've got blue and another angle that's a linear pair, well, it better be green too. Linear pair theorem, baby. LPT. If this is a linear pair and this is a linear pair and I know that one's green, well, this one better be green too. Same reason here. This is a linear pair, blue and green, and I know blue and whatever is a linear pair, so this one must be green as well. Also vertical angles, right? So just because these are parallel, we get all this for free. That's kind of nice. If they weren't parallel, we don't get that. Let me show you that. I think I can show you by a quick example. Here's two lines that I think we both agree are not parallel. And if I was to draw a transversal, remember transversal is any line that intersects another two. Technically, this is a transversal too, because it's going to intersect this one and it already intersected that one. But we'll focus on this as our transversal. I think it's very clear to see that alternate interior angles are not the same here, right? Ain't gonna happen. Alternate exterior aren't the same either. This guy is still the same as this guy, because that's vertical. That happens anytime, right? Anytime we have an X. And this guy, let me recolor him because he's not purple, would be the same as this guy, because again, vertical angles, right? But they're not necessarily gonna match. Amazing, majestic. All right. That was yesterday. But today is a new day. I use L and M because L for line and M's the next letter. I don't know. They use cursive to denote lines. Points are done with like capital letters, like point P, point D, right? Capital print letters. That was good. That was good. Now, I haven't told you these are parallel yet, so you can't assume that, even though they look amazing. I'm going to call this line N, and I'm going to call this line P. I don't want to call it line O, because O's look like zeros, even though I put a line through mine. I'm going to tell you that they are parallel, though. I'm going to do a little arrow symbol here. So that tells you N is parallel to P. And I'm going to tell you that this is parallel to L. Now, the way I've denoted this makes it look like, well, M is parallel to P because they both have one arrow symbol. And that ain't true. So what I'm going to do is another arrow to show these are the ones that go together. So I know L and M are also parallel. Now, given this information, what can you tell me about these angles? 1, 2, 3, 4, 5, 6, 7, 8. Normally we'd use letters to label these, but like, good God, that would take forever. 9, 10, 11, 12, 13, 14, 15, and angle 16. They got a little darker for you. There you go. A little bit easier to see. Or worse. Paul, how about you? You're in the cheap sheets. Easier to see? Okay, good. I feel like I'm at the optometrist. Number 1 or 2? 2 or 3? 4 or 5. 5 or 6. Could do an ASMR channel. ASMR, I'm your optometrist during COVID. All right. What do you know? And how do you know it? Chase! Ooh, they are alternate. Are they alternate interior or alternate exterior? Yes. Yes, they are. They're both, right? We got one exterior, one interior. Okay, sure. What about them? We could call them that. Sure, we could identify them as such. But what about them? What you got for me? Somebody. Anybody.
Somebody should put a straight jacket on this guy!
When am I ever going to use that? I don't know. The Iceman from downtown. There's a lot of lines here, isn't there? What if I cover up 1? Ah, that's a problem we recognize, right? Isn't that what we just did? 1 transversal, 2 parallels? What do we know? What about 1 and 4? Why? Crisscross applesauce, scissor theorem, vertical angles theorem, right? No matter what, those will have to be the same, because this is an x. It doesn't even matter that they're parallel. If we've got an x, we've got vertical angles. So we know 1 and 4 are the same. Same logic for 2 and 3, right? By vertical angles theorem, we know this. So if I was to write the proof out, I'd say by vertical angles, I know angle 1 and angle 4 are congruent. By vertical angles, I also know angle 2 and angle 3 are congruent. You can also say by vertical angles, 1 and 4 are congruent, and then by the same dumb logic, 2 and 3 are congruent. Save yourself some time. I love using same dumb logic. It just makes me feel fun. All right, cool. Now I know the same for all these too, but I'm not going to color those in because there's actually a connection between these and these. And I want to show that. I'd hate to do like red and purple down here and then later be like, oh, actually they're the same as blue, right? I'm going to hold off on that. How do we jump the pond? What's the connection between here and here? What do you see? I can't. What? How do you know 5 and 1 are the same? Same side interior? I don't know about that. This guy's exterior. That guy's interior. Doesn't mean they aren't the same. Yeah.
5 and 4 go together?
Do 5 and 4 go together? Why would you say that?
I remember the last one.
They will. Alternate interior angles theorem, right? Allows us to say that. Let's pretend for a second we don't know alternate interior angles theorem, because it's a theorem, we can prove it, right? Pretend you didn't know it, what alternate interior angles was. I know it's going to be hard to pretend that you didn't know it, because you did. You obviously, you knew it. You knew it so well. But pretend you couldn't remember what it was called, and all you remembered was the last one, that they're supposed to go together. Pretend that happened, okay? How would you prove that these two are the same? Might need to do some other stuff first. What does Euclid say about the postulate of parallel lines? If L and M are parallel, what do we know? They never intersect. That's true. That's a definition of parallel lines. How do we know they never intersect? What's his rule to figure out that they don't? This is amazing. I tell you the answer earlier and then I ask the question later. Fantastic. I love it. If I distract them long enough with a stupid story or something dumb with NBA Jam, it comes out of their brain, and that lets me know you never learned it in the first place. You think I'm doing it just to be silly, but nope. It's a test. Okay, fine. What do you know about 4 and 6? 4 and 6. Angle 4 and angle 6 to be specific. They're what? They are interior angles. You guys are good at naming them. You're not good at telling me what they are or how they relate. They're same side interior, right? Not alternate interior. Right. Same side interior. And same side interior angles, according to Euclid's postulate, right, the fifth postulate, will always be supplementary. If the lines are parallel, then these guys are supplementary. What does it mean to be supplementary? Yeah. There you go. So we said by vertical angles, these. We'll say by the fifth postulate, you can say by the parallel postulate if you want. Use a little parallel symbol, parallel postulate. We know that 4 and 6 are supplementary. In other words, they add up to 180. That's an ampersand, an and symbol. I love when people call it an and symbol. Supplementary. Now, if 4 and 6 are supplementary, what color must 6 be? Yeah. Green. Why do you know it's green? Because it's small. It looks like it goes with it. Looks can be deceiving, Parker. Just because it looks small doesn't mean it is. How do we know that 6 is green? Yo, Chase, oh, nope, he gave up. It's like, nope, never mind. Faking me out. Because blue and green are what? A blankety blank. LPT? Since angle 3 and angle 4 are a linear pair, linear pair, LPT is linear pair theorem. By linear pair theorem, they must be supplementary, right? That one was a better one. Well, if 3 and 4 are supplementary and 4 and 6 are supplementary, it means they both add to 180, yeah? If they both add to 180, then they add to themselves. So I can say this. Ooh, I don't know this is green yet. Right? It's 3. Oh, nope, we do know 3 and 4. This is the one I don't know. My bad. So 3 and 4 are sup. And 4 and 6 are sup. And 6 is the one we don't know about, yeah? Colors are hard. From this, what do I gather? Therefore what? Chase?
3 and 6.
3 and 6 are the same, and now I can call them the same. Now, typically when we use equal signs and plus signs, we're talking about the measure of these guys, so we put a little m to say the measure. If we're talking about the ideas, they're congruent. So 3 and 6 are the same angle. Another way we can say is their measures are the same. I get used to using congruency eventually. So the ideas are supplementary, the ideas are supplementary. That's fine. Actually, let's make that angles, right? The length, the size of them are supplementary. So 3 and 4 are a linear pair. That means their measures are supplementary. And if their measures are supplementary, then they must equal each other, because they both equal 180. That means the angles must be the same. So we've jumped the pond. Congratulations. 6 is green. Tell me what else you know. 7 is green by? Yeah, Scissor Theorem, right? Where is it?
Your words, not mine.
Vertical angles theorem. Some Scissor Theorem, they're the same. VAT is vertical angles theorem. I'd write that down here and say, therefore, 6 and 7 are congruent. What else do you know? 5 and what? 5 and what is blue? 5 and 8 are blue. Why is 5 blue? So 5 and 8 are the same. We agree, right? But I don't want to mark that yet because I know that 5 and 4 are actually the same. I want to mark them both blue. If I just say they're the same, then I have to mark them both purple and maybe later turn them into blue when I realize they're the same, right? So I want to hold off on that. But I do know they're the same by vertical. But I know 5 is the same as 4. And the reason I know this is because 4 and 6 are supplementary, right? They both add to 180. Aren't 5 and 6 also supplementary? Why are they supplementary? Yeah.
They're on that line.
Yeah, they're a linear pair, right? They're a linear line pair, right? And if 4 and 6 are supplementary, and 5 and 6 are supplementary because they're a linear pair, well then, the number you add to 6 to get 180 will be the same number you add to 6 to get 180 here, right? Oops, wrong color. So 5 and 6. Very similar to what we did here. These two are supplementary. These two are supplementary. That means this plus this equals this plus this. Subtract 6 from both. These are the same. Instead of getting this, we get 4 and 5. Cool. So, but you could say by the same dumb logic, 4 and 5 must be the same. Saves you a lot of work. And then 5 and 8 are the same because... What's the easiest way? Vertical angles, right? Could you do it from linear pair? Yep. 6 and something makes 180. 7 and something makes 180. 6 and 7 are the same, so 8 must be blue. Right? Something like that. All right, we jumped across this pond. What about this guy? Where are your gods now? When God gives you lemons, you find a new God. Yes?
9 and 12 together.
9 and 12 go together. That's true. Do they have any connection to these guys? Yes or no? What do you think? Make a conjecture. His conjecture is yes. Now we either need to prove that conjecture true or false. Well, 9 and 7 relate to these guys in any way. We know they're congruent because vertical, right? The question is, are they both purple or are they both green or blue? Two and 9 are supplementary. How do we know that? Ooh, how do we know that? Supplementary means they add up to 180, but how do we know that they add up to 180? I'm gonna give you guys a hint. Ta-da! Do you see how it's the same problem we had earlier? Internal, same side interior angles are always going to be supplementary if the lines are parallel. And they are. Look, this is parallel to that. Here's our transversal, right? Two lines, transversal, interior angles, same side interior angles will be supplementary according to Euclid's fifth postulate. So by the fifth postulate, 2 and 9 are supplementary. Well, if 2 and 9 are supplementary, and 2 and 4 are supplementary, then 4 and 9 must be the same. It's this all over again, right? Ta-da! By same dumb logic, 9 must be blue. 9 and 4 are congruent. What else do you know? 12 vertical angles, yeah? 11 and 10 go together, that's true. And you said it's green. How do we know it's green? Chase.
Because it's like 11's like the over there.
It is like the 3. That's true. 9 and 11, too soon. 9 and 11, they're going to be supplementary. Why? Hi, Annie. Say again. They're a linear pair, aren't they? So 9 and 11 are supplementary because linear pair. 2 and 4 are supplementary because linear pair. Aren't 2 and 9 also supplementary? So that means this guy must also be green. Must be the same as 2. 9 and 2 are supplementary. 9 and 11 will be supplementary. I want you to fill out the rest of this, write a blog post about it, explaining why these all are. I want you to do your best to do this. Now, here's the thing. This is a pain, but you got a video to go back and look at. 1. 2, write it out on a piece of paper instead of trying to type it. Take a picture of it, okay? See you later. Daniel!
Why are you holding them with your phone?
Oh, you know, it's how I be. You see what we're doing? You wanna come on in?
No, I gotta get the class.
Oh yeah, don't be late. Hi, Olivia. No peeking. Alright, I'm gonna spray down desks. I'll be back in a second, guys. You need to get individual mics for every single desk. That's the dream. That is the dream. Yo. I can take my little boy. You just think I love that. It's like, that's funny. What I do was funny. Hello.
Hi.
Hello. Did you straighten your hair extra today? Did you get more hair recently? What happened? Okay. Hello. Hi, Sarah. Hi, Dave. Use the restroom. We'll be with you guys in a second. I want you to recall what we did talk about yesterday online. We'll review it and then go to the next step. Talking about the fifth postulate and its implications today. What's up, everybody? All right, who do I see? I see Annie. I see Blake. I see Olivia. I see Jaden. I see no Theron yet. Do I see Shion? I do see Shion. Marissa. No Marissa yet. Do I see Katie? So Katie, it turns out you're a big fan of the Beebs, like in real life. I didn't make that up yesterday. That's like actually real. That's what everybody tells me. Jaden. All right. Marissa's here. I see Campbell. Did I get Corinne? Corinne is here. Okay. So just missing Theron right now? What it looks like. All right, so Theron, while you're getting here, I want to review what we did yesterday. Remember fifth postulate and all that stuff. So as you recall, the fifth postulate, your favorite postulate. What about the other four? We didn't talk about that. They're kind of boring. Like, one of the postulates is if you have 2 points, you can make a line. And it's like, yeah, you can't prove that. We're just going to, like, sure, right? Another one's segment addition postulate. If I had 2 segments, I can put them together and make a big segment, right? And it'll be their lengths added together. So, not that interesting. We'll use segment addition postulate occasionally. The most interesting one by far is the parallel postulate, the fifth postulate. A postulate that Euclid thought he could actually prove and become a theorem. And so he waited really a long time before getting into it in his book. And then eventually he's like, okay, look, I can't prove this. We're just going to have to accept it to be true, because if it wasn't, things would get weird. In fact, they get so weird, they call it non-Euclidean geometry. Assuming that this is not true, you get really weird results. Weird results that actually describe our world pretty accurately. We talked about this yesterday online, I think. Did I pull out the globe in here? The second hour I did? Right? Straight lines on a globe are actually curved, right? If I were to tear off the map of the globe and then lay it flat here, those lines would curve. They wouldn't lay straight. And curved lines on here if I laid it out flat, would become straight. So it turns out, if the world were round, and I think it is, this geometry would be less accurate. Straight lines would actually intersect because they curve. Something like that. We call it non-Euclidean geometry. You get a lot of weird results. In math, we are not just assuming things to be true all the time. We do take leaps of faith, but we also say, but what if not, right? What if this weren't true? An entire form of mathematics was born out of it, and it turns out it describes the universe very accurately. Because not only is the Earth round and curved, but space-time is curved and round. Space is not flat, it is curved. And what I mean by that is, I think I talked about this yesterday, imagine a trampoline and a really heavy bowling ball on one end of it, right? Trampoline sinks in. Now imagine a golf ball that you put on the other side. What's going to happen to that golf ball? It's going to roll towards the bowling ball, right? It's going to roll towards the bottom. So Einstein says this is what space is like. Heavy object, like a planet, bends space around it. The fabric of space is the trampoline. And the reason gravity happens is because they want to roll towards the bottom of it, right? Things roll towards it. That's what gravity is. But it turns out space is curved, and it curves because of really heavy things, really massive things. So Euclidean geometry actually doesn't work at really big scales or really tiny atomic scales. The world is actually better described by non-Euclidean geometry, but we're going to learn Euclidean geometry because it's fun. Yay. And it's a good start. Much easier to wrap your head around non-hyperbolic space and just assume we're in flatland. We'll do that for now. Can you imagine? Every time I wanted to draw a diagram for geometry, I had to bust this thing out and draw it on here. That'd be awful. Thank God for paper. All right, so this thing right here. The fifth postulate says that if you have two lines, we'll call them L and M. The reason we use L is because it starts with line, L, right? I just chose it. And the reason we use cursive is because regular print letters are reserved for points. We'll call this line T. It's a transversal. A transversal transverses, meaning it goes across. A transversal is anything that goes across two or more lines. So L is not a transversal because it only crosses one line. But T is a transversal because it crosses two. Oh my gosh. Yeah, it reminds me. This is our last day on YouTube. After this, we'll be moving over to Google Meets. Google Meets has updated their features to the point where I'm like, you know what? This will work. I can do the picture-in-picture. I can get everything except a couple things. So we're going to move over to that.
So instead of a live stream, you're on Google Meet?
It'll be a live stream, but it'll just be through Google Meets instead of YouTube. I'll send you a link.
Like we have a Google Meet link on the top.
Yeah, that's what we'll do. That's what other classes are doing. The only problem is that Google Meets is still kind of slow. Like, it's not a delay like it is on YouTube necessarily. That's really nice. But like the quality of the picture's kind of bad and the sound's kind of bad. But it's gotten to the point where I think I can tweak it. I've got a couple different programs that I've worked out. I think it'd just be better. It sucks for you guys because Google Meet, you have to have the code to get in, right? And if you forget the code or don't have the email or something, it's like, what do I do? Whereas YouTube, you can just Google it. That's true, and that should be easy, right? Because now that they have that, that's going to work out. They didn't have that back in the spring, but they do have that now, which is really nice. And I didn't realize they had it. Hi, Theron. I was worried about you. Don't worry, I stalled. So, fifth postulate says that if we have two parallel lines, and those are marked by these symbols, right? Little colored in arrows. That tells us that L is parallel to M. Then we know that the same side interior angles, these two, won't be congruent necessarily, but will be what? What do we know about these two angles? Euclid's postulate says that if this, then what about them? Nope, not the same. Congruent means the same. What does he say about them? Now remember, if we were to draw a straight line, and we said straight yesterday was 90 degrees straight up, we have 90 and 90. It's not that they're congruent. What do 90 and 90 add up to? 180. These will always add up to 180 if these lines never cross. And the reason for that is because you could measure straight up and compare, and as long as this height is the same as this height, then the lines must never intersect, right? But Euclid says you can also do this. Instead of measuring my two hands to see if they're the same height by putting them back to back, I could also just do this. And as long as they're leaning the same amount, then it's clear they're the same height. If I do this, well, then one hand looks bigger than the other, right? As long as they lean the same amount. And by same amount, what he means is the two angles that they form with the ceiling and the floor are supplementary. That's how he says it. Euclid's pretty wordy. So, in other words, we know this. What's the definition of supplementary? What does it mean to be supplementary? Say again? Not opposite necessarily. I think you're thinking of alternate. We talked about that yesterday. Alternate, right? Like these would be alternate interior angles. What does it mean to be supplementary? No idea? Okay, then I'll tell you the definition, just so you know what it is. By definition, supplementary, the definition of supplementary means that these two angles add to 180. That's all, just another way of saying it. I think you were thinking too hard, right? So those two angles are supplementary. That means the measure of those angles. And the way we say measure of those angles, we put a little m. You can't add two angles together. Two angles are ideas, but the measures are numbers, right? And they can add up to a number. So we put little m's to say we're talking about their measures. Cool. So they'll always add up to 180. That's the fifth postulate. Now what's cool about this is that we've got an A, B situation. Here's A. If they're parallel, then B, don't you touch Corinne's stuff, they're supplementary. What a liar. Wow, Ethan. Wow. Disrespect. Corinne, he's touching your stuff. It's Ethan Schroeder. He lives at 555. No, okay. So, A and B. If A, then we get B. We talked about this yesterday. The idea being, like, in real life, this is an implication. It implies something. You might say, if you play dumb games, you get dumb prizes, right? Playing dumb games makes you get dumb prizes. Now, the reverse for that is not necessarily always true. You get dumb prizes, it means you must have been playing dumb games, right? Sometimes life's just like that. It doesn't always go both ways like this. However, this one does, and it's kind of interesting. So this postulate goes both ways. If it's parallel, then these are supplementary. It also goes the other way. If these are supplementary, then you know these lines are parallel. And that's really useful, because as soon as we know we have parallel lines, we get a lot of interesting things. How do we feel about this? We feeling okay? It's a postulate, right? The parallel postulate, the fifth postulate, whatever you want to call it. So you have to accept it to be true. You can't prove it. But it makes sense. If this was bent anymore, right, it would eventually intersect down here, right? These angles had to be supplementary. It makes sure that they never touch. Okay? And it goes both ways. If those don't touch, then these are supplementary. Other way around, if these are supplementary, these don't touch. Fifth postulate. Cool? What do you use? Why is it so shiny? How do you do this? We're like in the middle of fall / winter. It should be like getting darker, and here you are just like... I used to be blonde. Can you believe it? I used to have hair. Can you believe that? My kids last year called me Rogaine. Shout out to Alex Anderson. All right, so parallel lines get us some really interesting things. What kind of a line is this? What do we call that? What kind of line is the gray line? It crosses two others. I love how I tell you the answer earlier and then I ask it and you can't remember it. And it's because I distracted you with a funny story. And you think I'm just doing it because I'm weird and I'm, you know, a goofball. But in reality, I'm just trying to distract you so I can ask the same question I asked earlier and get, you know, more mileage out of it.
It doesn't stick.
I know. And it definitely doesn't stick when I make you think about something else. And that's how I know you don't know it yet. Isn't that great?
Like I know it.
I know, isn't that wonderful? And now you have a memory of forgetting it, which means you're going to want to remember it now? Yeah.
And this isn't very big.
Ooh, no. Congruent means they're the same.
Okay.
Right? So like two ideas being the same, like this angle is congruent to that angle means they're the same angle, right? Just in a different spot.
Doesn't it start with T?
It starts with a T, yep. I appreciate the guess though.
And
Trans means to go across, right? Transverse. Transversal, yep. To transverse something, we go across it. So this is a transversal. It goes across two other lines, sometimes more. This guy we don't call a transversal, L. We don't call it a transversal because it only crosses one line. Not as interesting. But we have a transversal and we have two parallel lines. We get a lot of interesting properties out of that. First of all, since these are parallel, that was given to us, right? I told you they were parallel. That's what this means. What does Euclid's fifth postulate say? Let's number these guys. What does Euclid's fifth postulate say has to be true if those lines are parallel? Exactly. So 6 and 4. We'll make this green, we'll make this blue. Could they be equal? Sure, they could. They could both be 90, right? Do they look like that in my diagram? No, but looks can be deceiving. Remember this guy, right?
Take it easy, assistant drawing.
So we know that angle 6 and angle 4 must be supplementary. Now, if you wanted to, you could say, therefore, they equal 180 when you add them together, right? So let's do a little therefore symbol because it's cool looking. If I add them together, measure of this guy and measure of that guy equals 180. This is what proofs are like, guys. It's writing down your reasonings. That's by definition. So maybe you want to put your reasoning. How do we know that supplementary is 180? By definition. Right, it's a definition of what it is. How do you know that's a dog? Well, it fits the definition. It's a furry animal that walks on 4 legs that is man's best friend. Right? So that's why we're allowed to call it a dog. How do you know this is called 180? Well, it's because that's the definition of supplementary. Right? By definition, you're going to be using that a lot. Okay, cool. So we know that. But I told you parallel lines are really useful because they get us lots of information. That's good. Because as soon as we find parallel lines in a diagram for a really tough problem, boom, 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 we get tons of free information, which allows us maybe to solve that problem. So we get this, but what else do we get? What else do you know about these angles? And hopefully you can explain why. If you can't explain why, I'll have somebody else explain for you. 5 and 3 must be supplementary. Same dumb logic, right? Right? Euclid's postulate says same side interior must be supplementary. Aren't these same side interior? Just because you like the right side better than the left side doesn't mean that you can't do it for both, right? So yeah, we know that these are supplementary. Now I'm going to wait a second to write this down. But if I would, I'd say by same logic, right? Same thing I did before. Save some ink. By the same dumb logic, 3 and 5 must be supplementary. Now here's the thing. If I use color to denote which ones are the same, I can't mark this green or blue yet. Because I don't know that they're the same as these guys. All I know is that these two add up to 180. That's all I know. So I could do like orange and pink. But the thing is, spoilers, these guys are related to these guys. I'm going to want to use blue and green. So I don't want to do orange and pink and then have to go back and change the color. So I'm going to wait to write that. How do we know 3 and 5 must be green or blue? In other words, how does 3 relate to these guys? How does 5 relate to these guys? What do you know? Opposite? What do you mean? Like here and here? Yeah, they are. We have something called alternate interior angles theorem. It's a theorem, so it's proven. That says the alternate interior angles, interior meaning on the inside, alternate meaning opposite sides, right? That they will be congruent. So this will be blue and this will be green. Now, it's a theorem. So eventually someday you'll be able to cut to the chase. Look, alternate interior angles theorem, moving on. They're the same. But right now, since it's a theorem, how do we know that that theorem's true? Should be a way to prove it. So pretend we don't have alternate interior angles theorem. How are we going to prove that 3 is blue? How do you know 3 has to be blue? Its relationship to 6 is alternate interior angles, so we can't use that. I told you we're going to wait on that. So it must have some relationship with 4. What's 3's relationship to 4? What? Parker Porin, I love how geometry is the only math class where most of my answers come by miming. But Parker Porin was like this. And we guessed for a while what he meant. I said, how does 3 relate to 4? And he did this. What do you mean by that? It's an international sign. You got to know this. I mean, come on. Why? Who said that? Like ventriloquism in here.
Not me.
And it's not because you're a bunch of dummies. Sarah? Why do 3 and 4 equal 180? How do you know that? Oh, because they're a straight line. How do we know that an angle for a straight line makes 180? I'll tell you why. Here's a straight line. I know this has to be 180 because it's half a circle. And what's a full circle? 360 no scope Snoop Dogg, right? Call of Duty. That's how we know it's 360. There's your proof, right? Call of Duty, 360 no scope, aim assist. It's half a circle, so it's 180, right? So this altogether must be 180? We have a name for two angles that make up a line. We call them a linear pair. Linear because line. If something is linear, it means it's like a line. And pair because two, not like the body type, right? So linear pair is what these are. So we're going to say bilinear pair theorem, because 3 and 4 are a linear pair, right? They're together on a line. I know that angle 3, which I'm going to leave black for now, and angle 4 are supplementary. Are sup, not sus, sup. Supplementary. Now, by definition, what does supplementary mean? So the measure of angle 3 plus the measure of angle 4 equals 180, right? That's by definition. Okay, cool. So we know that 3 and 4 are supplementary. I don't know what color 3 is, but maybe I can figure something out. What do you notice about this and this? Which means this must equal that, right? So we're going to substitute. Instead of saying the same statement over again, that 6 and 4 makes 180, I'm going to say 6 and 4 makes this. I'm allowed to switch out 180 for this because, look, 180 and that are the same thing, right? Whenever I see a 180, I can switch it out for this. I see a 180, I'm going to switch it out. We call that substitution. You know what a substitute is, right? Right? Like a switch out, a switcheroo, right? When I'm absent, they bring in a sub. And again, the whole idea of a substitute is they have to be the same. See, this has to be the same as 180. If it is, then I can switch it out for 180. Just like a regular substitute. They come into the room. They could be me. I mean, there's really no difference, right? You would agree when a sub's here. There is no difference between me and them. They're basically the same thing. In fact, I could be a substitute right now. You wouldn't even know.
Are you?
By substitution, I can write that the measure of angle 6 plus the measure of angle 4, instead of writing equals 180, what can I set it equal to? Measure of angle 3 plus measure of angle 4. Ooh, you're getting excited. Calm down. Just math. All right, so if this is true, what does that imply? Therefore, well, they both equal 180. We already said that. Go ahead, Haley. Not sure? Well, oh, okay. If you ever want to say something but you can't explain why, that's fine. Somebody else might be able to. Or if you have a little bit of it. But if you completely forgot, I understand. That happens. I appreciate you trying. If I say 5 equals 5, and I subtract 3 from both sides, I get this, right? I'm not a crook. True statement before. After I subtract 3 from both sides, is it still a true statement? It's a different statement, right? 5 equals 5 is different than 2 equals 2. But it's still true.
Oh.
Haley?
Is it like that angle 6 plus
So I subtract the 4 from both sides, and look what statement's left over. Can you read that statement for me? Very good. So therefore, by algebra, essentially, it's called the subtraction property of equality. If you have an equality, you can subtract from both sides, and it'll still be an equality. Measure of angle 6 equals measure, and now I can use blue. Angle 3. Another way I can write that is I can write it that this is true. The measure is the same, meaning that if they're 90, they're both 90. If this is 60, they're both 60. But if I want to just talk about the angles and say they're literally the same angle, just in a different location, if I'm talking about the ideas, I'm going to use congruency. That's what that means. Those two angles are congruent. The ideas are the same, right? Numbers can be equal. Ideas are congruent. Does that make sense? It seems kind of silly that we have to draw a distinction, but it helps later on, okay? Are we cool with the idea of congruency? Measures are equal, ideas are congruent. So 6 is the same as 3, which means I can use blue. So basically what we said is, look, this right here makes 180, and I know these make 180. Green and blue always make 180. So if I see green here, well, then that better be blue. Let me prove it to you mathematically. Let's make up a number, right? Say this is 140 degrees. This one has to be what then? Math is hard. 40, right? Because they're supplementary. Well, I know these are supplementary too, so they must add up to 180. 140 plus what gets me 180? See how these are both 40? Right? They have to be. Yeah, I love it. So you're saying by the same dumb logic, the same concept, this must be green. If these are supplementary, I'm sorry, let's say this again. If these are supplementary, and these are supplementary, blue and green are supplementary, blue and, well, green, it has to be green, right? There's no other number you could add to 40 to get 180, right? The only number it could be is 140. So in order to save some time, and to show that you understand that we're doing the same thing again, not only are we saving time, but we're actually showing better understanding. You can say, by similar logic, I usually use the same dumb logic. By SDL, we know that 5 and 4 are the same. So I'm going to write 4 congruent to 5, and I can do it in green because they're the same measure now. When you do this for your portfolio, don't try to write this out in bulb. Oh my God. First of all, angle symbols, congruency symbols, plus signs, it's not going to like that. It's not meant to talk about math. Write it out and take a picture. That's the better way. Yes, you're going to have to write proofs, a lot of proofs in geometry. That's what we're doing right now. We're just backing up our reasoning. That's all proof is. Regular math is the answer's 5, and we go, yay, okay, move on, they guessed right. Even though maybe in your head you accidentally got 5 right. But in geometry, you have to say, okay, but why is the answer 5? Why are these congruent? I know they are, but why? And that's where this comes in. You have to write about your reasoning. So we've said, since these are parallel, we get 6 and 4 by the first postulate, or the fifth postulate, right? Since these are supplementary and these are supplementary, well, then these are both blue. They gotta be, right? We did some substitution, some subtraction. Then we said by the same logic, well, if these both are blue because supplementary and supplementary, then these both are going to be green because supplementary and supplementary. Ta-da! We've got all our internal angles taken care of now. And we've proven alternate interior angles theorem. If we have two parallel lines, that's all I said. Didn't say anything else about them, right? They're just parallel. I automatically know this is true. It takes a while to get there, but I know this is true. Alternate interior angles, alternate sides, interior angles will be congruent. Alternate interior angles theorem. Theorems are nice because they let us skip all of this. It's already been proven. The theorem says they're congruent. But pretend you don't remember what alternate interior angles theorem is. Or maybe I say, you're not allowed, I want you to prove it. This is what you can do. It's a theorem because there is a way to prove it. So even if you forget it, you can come to the same conclusion. You just prove it all over again. What about our external angles? 1, 2, 7, and 8. What do you know about them? What do you think you know about them? What? Which will be 180? Give me specifics. 7, 8 will be 180. 1 and 2 will be 180. In other words, they're what? What's the LP and LP theorem? Nope. LP. linear pair, right? See how they're a linear pair? Together they're on a line. They're a linear pair. Linear meaning line, pair meaning two. You dig? So linear pair theorem says that they must be 180. They must be supplementary, which means they're 180, right? Cool. So 7 and 8 have to add 180, 1 and 2 have to add 180. Fantastic. What else do you know? That doesn't give me any colors, right? So I'm going to not write that down. Seven and 6 are the same because why? 7 and 6? They add up to 180? I think you're confusing the terminology. What does he really mean? They're not supplementary necessarily. What are they? Starts with a C. It's this guy. Congruent, right? 6 and 7 are congruent. How do we know 6 and 7 are congruent? Haley, help him out. Scissor theorem, right? Whenever we have an X, the top and the bottom will always be the same. We call it vertical angles theorem because the vertical angles will be congruent. Technically, the horizontal will be too, right? Naturally. How do we know this is true? It's a theorem, right? We can prove it. You have to do it. Well, you will have to do it. You got to beat it, kids. How do I know that those two angles are the same? Well, let's pretend they aren't the same. I need more colors. I'm running out. Can you guys tell that's pink?
No.
Not at all. The color is really bad on this. Does it look like a different color, though, than red? It does, doesn't it? Okay. So how do I prove these two are the same? Well, vertical angle theorem already did it, but how do I prove that vertical angle theorem is true, right? Well, what do you notice about these two angles? They're a linear pair, which means they're equal 180, right? By linear pair theorem. So green and red make 180. What do you notice about green and pink? They're also linear pairs, so they equal 180. Green and red makes 180. Pink and green makes 180. Subtract green from both sides. Green equals pink. I'm sorry, red equals pink. Colors are hard. Right? Are you digging that? You want me to show it? You want me to write it? Sarah's like, no, please God, no. Stop. Okay, Sarah. This time I will spare you. So 6 and 7 are congruent by vertical angle theorem. Oh yeah. Oh yeah. What about 2? Angle 2, what do you know about it? 3 by what? How do we know? Scissor theorem, right? You can use that or you can call it vertical angles, doesn't matter to me. Whenever you use scissor theorem, I usually say this. Your words, not mine. Alex Anderson came up with scissor theorem last year. He's like, so you're telling me these two angles are scissors and that means they're the same? And I was like, your words, not mine, kid. Ask Alex about that sometime. All right, so 3 and 2 are the same by vertical. Also, instead of using vertical angles theorem, which is like the shortcut, how do I know 2 and 3 are the same? What's another way I can do it? I love this. I just did it, and then Haley. 3 and 4 are a linear pair. 2 and 4 are a linear pair. Well, if 3 and 4 are paired together, and 2 and 4 are paired together, then 2 and 3 must be the same, right? Blue and green always go together for 180. Green and something must go together as well. Well, if green and blue always go together, then that must be blue as well. Thing we did over there. Something subtract, and that's what Jace was talking about, right? So vertical angles, or you could prove vertical angles all over again if you wanted to. So by vertical angles theorem 2 and 3, by vertical angles 6 and 7 congruent. I'd write that down here. By vertical angles theorem, VAT, or scissor theorem. We know that 6 is congruent to 7, 2 is congruent to 3. What about 5 and 8 and 1 and 4? Yeah. By vertical angles theorem. Or you could do supplementary, right? Linear pair between these two, linear pair between these two. If green and blue go together here, then blue and green are going to go together here, right? All right. That was yesterday, more or less. I'm glad we reviewed it. Remember, there's always a where are your gods now problem. Oh, that's good. That is good. Look at that. I'm going to tell you that L and M are parallel. I'm also going to tell you that N and P are parallel. I didn't use O because those look like zeros. We use cursive letters for lines, right? Cursive lowercase. Now, I'm also going to tell you N and P are parallel, but if I do this, do you see how it looks like I'm saying that P and L are parallel because they both have the same symbol? Right? So in order to avoid that, because that's definitely not what I'm trying to say, I use double arrows here. Okay? So this implies that L is parallel to M, and N is parallel to P, and the two so never mix, right? Let's label some angles. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 angles, baby. Like 16 candles, but less romantic. You guys ever seen that movie, 16 Candles? You would. I've never seen it, actually. Is it good? Yeah, okay. I'll have to check it out. In fact, let me write that down. I have a giant note for movies I need to watch on my phone, including all the band names. I told you about the band names I came up with, right? No? You guys want to hear some band names that I came up with just from conversations that I've had? I'm like, ooh, that'd make a good band name. All right, here we go. Some of these are better than others. It's because I've been with people and they're like, oh, you have that list. You should write that down. And I go, oh, yeah, okay. So blame them, not me. Here's some band names. The Kitchen Kettles, Infinite Bison, Liquid Pain, spelled with a KW, Ant's Van. I came up with that one. Ant's Van, like an aunt. Ask Taylor Swanstrom about that one. That was a great day. Cosmic Granola, Unknown Leg, Pink in the Hypotenuse. Happened in math class. Hot Sauce Lollipop, Universal Deodorant, Jumbo Shrimp. That's a great band name. Caged Tarantula, Dumb Out Loud, Tater Tot Casserole, Intentionally Dessert, Stabotage, Blackberry Catastrophe, Tattoo Grandma, Oboe Seduction, like the instrument, Polyamorous Nightmare, exclamation point, like Panic at the Disco, Birthday Cards, Soda in the Coat Pockets. I rest my case. If you find any good band names, please send them with me. You gotta have these things at the ready when you tour. Let me tell you, coming up with a band name sucks. You love those? I love you, Mika. All right. What do you know? Given that these are parallel, I told you we'd come up with a lot of information, and I distracted you from the last one. You thought I was just doing that. Isn't that great? I love that. I love when I do that. You're so easily distracted. Jace, what do you know?
I know. 1, 2, 3, 4, 1, they all equal 180.
Good, so we have a lot of linear pairs. 1 and 2, 1 and 3, 4 and 2, 3 and 4. Wonderful. What else do you know? Haley.
There's a lot of linear.
There's a lot of linear pairs. Wonderful. Haley, is Haley short for anything? I feel like it should be. We need to come up with a way. I made Macy short for Masandra. Haleyandra doesn't really sound as good, though. I'll think about it. Say it again? Ooh, they are transversals. If I cover this up, this is a problem we understand, right? We have two parallels cut by a transversal. We get lots of cool things. What do you get? What do you get? What do you get? Sarah, do you want to say something or no? Okay, great. She doesn't want to say anything. Sorry. I'll never call on you again. I don't want that look.
Wow.
All right. What else you got? What do we know if they're parallel lines? Ooh, we do have interior angles and exterior angles. What do we know about? According to the fifth postulate, if we have parallel lines, then what? All lines are congruent, technically. All lines go on forever. They're all the same. They're just different locations. Right? When an angle's congruent, it means it's the same measure, but it's in a different location, right? lines are all congruent. Actually, every line is congruent to every line. It's not that. I'm blowing Sarah's mind. This is Sarah right now. For those of you that can't see in class, that's exactly what Sarah was doing. Sarah, calm down. It's just math. All right. What else do you know? Fifth postulate, baby. What does it say? Anybody online want to tell me what the fifth postulate says? Help these guys out. Don't rely on them. They will never save you. You wouldn't save them, let's be honest. What equals 180? 2 and 4 are a linear pair. We've already said that. Yeah, and that has nothing to do with them being parallel, right? Whenever I have a line and I have two angles, they're going to be a linear pair. What magic happens, according to the fifth postulate, if I have two parallel lines and I have one transversal? Right? It's Euclid's idea of how we know they're parallel. What do you know about angle 4 and angle 6? They're the same?
No.
They're different. Okay. What if my drawing was more like a square instead of a parallelogram? Then they would be the same, right? They'd be both 90. So they could be the same. They also could be different. But what do we know about them? Yeah, if one's 140, the other has to be 40. In other words, whatever they are, they must add up to 180. They must be supplementary, right? Euclid's fifth postulate says that if you have parallel lines, then the same side interior angles, same side because they're both on the right side here, right? Interior because they're on the inside. They must be supplementary. And vice versa. If these are supplementary, then these are parallel, right? It goes both ways. Remember that? So we know by the fifth postulate, or the parallel postulate, you can say this. By the parallel postulate, we know that 4 and 6 are supplementary. And you got to make them a color, so I just made them a color. Are sup, not sus. Supplementary. Cool. What else do I know? We literally just did this. I love it. It's literally the same problem, but I added a line to it. 3 and 5. What about 3 and 5? Same thing, right? By the same dumb logic. By the same dumb logic, we know that 3 and 5 are also supplementary. Now, before I write that down, just because these guys are supplementary doesn't mean they're the same as these two, but we know they are, right? How do I know that 3 is the same as 6? Three and 5 are sup. How do I know that 3 is the same as 6? Providing reasoning is what this class is all about, guys. This is what an assignment looks like, more or less. An assignment, if we're going to call it that. It's all about explaining. I know these match and crisscross applesauce and all that stuff. But you've got to be able to explain why. They're both supplementary because of the fifth postulate, right? But how do we know that 3 is the same as 6? Yeah, 3 and 4 are a linear pair, right? So they're 180. 4 and 6 equal 180 because of the fifth postulate, right? They're supplementary. So if these are supplementary and these are supplementary, subtract the one that's common, right? Angle 4 is common for both. What's left over must be the same. We'll say by LPT, linear pair theorem, we know 3 and 4 are supplementary. Y'all see that? There you go. And if 3 and 4 are sup and 4 or 6 are sup, what does that mean? Yep, it will. How do I prove that? Mm-hmm. Oh, I need a measure, don't I? Forgot M's. There we go. Oh, it's 6, not 4. Yeah, good call, good call, good call. That's why color helps. If I make a mistake with the number, we've got the color. If I make a mistake with the color, I got the number. All right, and then we subtract. So therefore, measure of angle 3, which I can now do in blue. Let's not even do measure. Let's do angle 3 is congruent to angle 6. Ta-da! How do we feel about that? 3 and 4 are supplementary. 4 and 6 are supplementary. That means they both equal 180. It means they equal each other. Subtract the middleman. Therefore, what's left must be true. So 3 and 6 are the same. Get used to that. If there are steps in this class, like a regular algebra class or something, this is the steps, I guess. It's different for every problem, but there's same ideas, right, that come up. How do I know 5 and 4 are the same? The same dumb logic, right? Now, I'm going to write same dumb logic, but you're going to tell me what the same dumb logic is, because I kind of helped you with that last one. Tell me why 5 is the same as 4. Nope. 5 and 4 don't equal 180. They're the same. They could both be 140 and 140. Why are 5 and 4 the same? It's the same reason why 6 and 3 are the same. Yeah, go ahead.
Isn't it like 5 and 3 equal 180? 3 and 4 equal 180, so you subtract it.
Subtract the common, and you get what's left over. Nice job. So by same dumb logic, we know 4 and 5 are the same. Is there a beep? Somebody hear a beep? I heard a beep. All right, we got our interior angles. What else do you know and why? This is going to be a post for next week, by the way. I want you to explain all these and how they're connected. Yep, all of them. Weirdo. 1 and 2 have to be 180 because they're a linear pair. Awesome. What else? That doesn't tell me any colors. I want to know which angles are congruent.
4, 1.
How are 4 and 1 congruent? Vertical angles theorem. Good. Your words, not mine. All right, so 1 and 4 are the same by scissors, but also because of these are 180 and these are 180. Cut out the middleman. These must be the same, right? That's how you prove vertical angles theorem, which you'll need to do as well, B-Day people, for next week. Prove verticals, right? Prove scissor theorem, right? You can do it. 2 and 3, same logic, vertical angles. Same logic here, vertical angles. Same logic here, vertical angles. Again, you could also just, you know, do the linear pair thing and then prove vertical angles. Oh, thank you, thank you, thank you. So you can get all these again with vertical, right? Or if you forgot, or if I said you're not allowed to use vertical, you could do it with linear pair, right? These are 180, these are 180, so this means these are the same, right? Yeah.
Well, I know you like 9.
Yeah, how do we get this? How do we jump across the pond? Go. How? Explain. Before I say yes, I want you to say it first, and then we can say same dumb logic later. Say it first. Explain. How do I get these guys now? Are these connected to these guys, or are they their own separate thing? What's your conjecture? Remember, conjecture is your hunch, and then we're going to go see if it's true or not. What's your conjecture? That these are connected to these, or that they're not? You say no? Why don't you think so? Because it's a separate line, right? That's a good reason. Does anybody think they are? Sarah? Was that a yes or no? Okay. Math is all about changing perspective. Sometimes that helps. M is our transversal now, and we have 2 parallel lines. What do you know about 2 parallel lines in a transversal? You get this, right? It's the same idea, isn't it? Haley, have I convinced you that they're connected? No? Okay, I'll try again. See how I have 2 parallels cut by a transversal, and that got them connected, right? Don't I have 2 parallels cut by a transversal here? So this and this will be connected? Better? Okay. Good conjecture, though. Because if this wasn't parallel, I wouldn't have two parallel lines, would I? And then they wouldn't be connected. Right? The magic is because I have two sets of parallel lines that I'm able to do that. You okay? Okay. So, how do you connect those? That's your problem. Work on that. Because once you get this for free, right? I want explanations. Watch the video if you need help. Seriously, you really need to for geometry. This can help. Otherwise, you're going to be typing like 12 paragraphs trying to explain what I did in like one. Okay? Getting used to being concise, mathematically speaking. Goodbye. Have a good one. Have a great weekend. I'll miss you all. Bye. We got everybody present. Oh, what's up, Tickler?
What's up?
Can we meet today to do portfolio stuff? Because you're really behind me.
Yeah, golf.
You got golf? Okay, that's not going to bode well. You're going to end up being ineligible because of a math class where you don't have any homework.
I'll be able to do like.
That's entertaining.
Yo. A band name could be Store Brand. I like that. Thank you, Theron. I come up with band names that happen naturally in conversation. That one wasn't really natural, but he was thinking about it. I'll give it to him. Uh-oh, we do? What's wrong?
I have a doctor's appointment after school.
Okay.
At 2:45.
That's not an issue.
Is it?
Nope, we'll do it Wednesday. Okay, I'll squeeze you in. I just don't want everybody doing that because I only have so much time for everybody to do 10 minutes at a time.
Just this part.
Yes, you should be good to go. Talk to the streets up in the office to make sure that you're fine, and we'll guarantee that. I'm not sure what happened because you never attended summer school like you're supposed to get that figured out. But you're in my class, so talk to streets and figure out. I think you're okay, though.
Oh, okay.
Wow.
Well, for summer school, I was told that I could do it at home, and so I did like stuff at home.
What stuff?
I did complete Spanish. Health.
But what about math?
I don't know what I did for math.
Exactly.
So I just.
Because as far as I'm aware, you didn't. So talk to streets and make sure you're okay, but I think you are. What? Oh. Hey, Skylar. Can I do my meeting after school? Annie, the answer is yes. It's going to be you and everybody, though, because a lot of people delayed, which means it's first come, first serve. So I'll send out an email. God willing, I don't get a meeting today that I didn't expect. I will be available starting at 2:30-ish. Okay? Unless I get a surprise meeting. Stuff like that happens because COVID and all kinds of crazy stuff, so we have meetings that pop up. Yesterday had nothing to do with COVID, but like, you know, sometimes I don't get free time like I plan. Rowan, I love your hair.
Thank you.
All right, Maddie's here, Skylar's here. Got volume. That's incredible. If I could wake up like that with hair, that would be amazing. Geneva, Lindsay, don't see you yet. I don't see Carter. Josh, Rowan, Max. Haven't seen Cliff yet. Nevaeh, Adam. Haven't seen Steven. So missing Carter, Steven, Geneva, and Lindsay right now. Bell hasn't rung yet, though. All right, today I want to talk about the fifth postulate. It's what we talked about yesterday. Just review it real quick and then get into what it implies. Fifth postulate, of course, is your favorite postulate. Duh. Right? Everybody's favorite's the fifth one. The other four are boring, right? Segment addition postulate, boring. Take two segments, add them together. It's the whole thing. 2 points, make a line. Boring. The fifth postulate's the interesting one. It's the one that leads us down a whole different whole different branch of mathematics called Non-Euclidean Geometry, which actually describes how space-time works. Did I mention space-time yesterday? You don't know. You weren't on the stream for real anyway. Ha 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 ha. Nope, I don't know. I don't know if I mentioned it in this class or not. Sometimes I riff, as they say. So, hello, Stephen. Today we're talking about the fifth postulate. There are only 5 postulates in Euclid's version of geometry. Remember, geometry is not just a study of shapes, but it's also an explanation of mathematics, right? It's a like a system, a structure that explains how math works. And the fewer postulates you have, or the fewer leaps of faith you're going to take, the more like structurally sound your mathematics will be, right? More structurally sound your geometry will be. And Euclid, a Greek guy, came up with a really strong structure for geometry, and we call it Euclidean geometry. And that structure is built upon 5 leaps of faith, only 5. What's up? School got shut down? What are you talking about? Hello?
What?
I don't know.
I already see it.
No, hang tight, hang tight. We'll see.
My friend got a call that I wasn't.
Yeah, tons of people. My mom called me and said the office put in something, and it was saying that no one was here.
Oh,
All
interesting.
students saying they were all going to like.
Maybe we
She
aren't.
called me in class. Yeah, my mom just told me, and she's like, "What?" Stuff like that.
Hi, Geneva. Hey, Lindsay.
That was so funny and that scared me.
There's like apparently.
I bet if I check my email, my
Oh, that reminds me. So today is gonna be our last day on YouTube. We're gonna switch over to Google Meets because Meets has finally gotten to the point where I think it's okay for teaching. Meets has an advantage of no delay time for people at home, right? So it's much easier to interact. And if you wanted to, God forbid, you wanted to like talk in class, you could do it. It's not closed here, unless you're talking about Sterling. Well, I don't know. We'll find out. But anyway. That's scary. I might have to grab all my stuff and take it home, which actually be nice because my internet is like 10 times better, more than 10 times better than the school. So anyway, we'll figure it out. But anyway, pulling it back. It'll be the last day on YouTube. We're going to switch over to Google Meets. The reason for that is because you can interact on it, and Google Meets is finally developed enough to where it's actually good for education, I think. Before it was I had to give you a link every day. Right, and that was a pain because then you don't get the link, or you use the wrong link or whatever, and you end up in the wrong class. And God knows we don't want to make it harder on you guys to show up, because when you do show up online, like, we should be rolling out the red carpet for you. Thank God they showed up, right? Let alone did anything else. I mean, just getting you to show up's a hassle. And I understand that's not an don't take that as an indictment of you, like, oh, they're lazy. I mean, everybody's lazy. I think the difference is that most of you guys are like, this isn't really learning or something. You're kind of revealing, you know, we can't sweep you under the rug like we used to. And you're like, this isn't worth it. But when you do show up, we should be rolling out the red carpet for you. And I thought Google Meets was kind of more of a hindrance than a help. YouTube, you can just Google my name and find the video, right? It has automatic upload, so you can watch it later if you miss it, right? All these things. I have a way now where I can work it out, so we'll be better.
Uh-oh.
Hi. No, it's cool. Yes. Rolling, Josh. So this will be the last day we do YouTube. We'll be switching over to Google Meets. I should be able to get like tiny me down here and the screen now. I figured out ways to get that done. So we're gonna do that. We'll use the links in Classroom like you've been using for your other classes in Google Class. Cool. That way I don't have to give you a link every time. This should be doable. Okay, is that cool? All right.
I got a candy bar.
Candy bar, all right. Thank you, Mr. Bielma.
Who wants it?
I do.
Josh.
Okay, just for a second. I know everybody hates their hometown and everybody craps on their school and everything like that, and everybody hates the principal because he's the principal, right? You know, but like, he's a good dude. He really is. He really is. He really
I
is.
mean, I've known him since I was like 3.
And I know and you know I can't say it if I hated him, right? You know, I couldn't, right? But like I wouldn't go out of my way to do this. I've worked at some really crappy schools, and I'm so thankful that I work for this guy. I really do. Every day. All right, so anyway, we're not gonna be on YouTube. Let's talk about the fifth postulate, the most important and interesting postulate of them all. Turns out if this postulate isn't true, it leads to a whole different branch of mathematics that actually describes space-time. We'll talk about that in a second. So the idea is this. Euclid struggled for a really long time with 2 lines being parallel. How do you know they never intersect? I mean, it looks like they don't, right? If they're perfectly positioned, but how do you know? How do you prove that? In fact, he tried to prove it as a theorem for a really long time, and in his book, he like waited and waited and waited. He didn't want to use this at all to prove anything because he's like, I don't know that this is true yet, so I don't want to use that to prove other stuff. That's not how I do things. That's not how I roll. I want 4 postulates, baby. But eventually, he's like, I can't. It has to be true because if it wasn't, I explored that. And good God, is that a nightmare? Non-Euclidean geometry, hyperbolic space. Oh my goodness. Okay. We're talking about 4th dimension stuff here, and Euclid's like, no, let's not. And so he's like, okay, 5th postulate, this. And here's what he said. He said, you know 2 lines are parallel, never intersect, if this is true. If you can draw another line that crosses them, We call that line a transversal. Trans, across, verse means to go, right? So transversal is what this is. It crosses two other lines. Now, all lines are transversals if they're not parallel, because like, look, this line right here intersects with this line. Is this a transversal? I mean, it is. But again, mathematics are interested in what's interesting. If all lines are transversal unless they're parallel, that's not very interesting, right? It's like, oh, it's a transversal. Great, just like all the rest, right? What makes a transversal interesting is that it crosses at least two lines. At least two. So this would be a transversal, but line L and line M would not be considered transversals, okay? That's all. It just makes it easier to draw a distinction. So Euclid says two lines are parallel if you can draw a transversal between them and the interior angles, the same side interior angles, like this angle here and this angle here, are supplementary. Now, what does it mean to be supplementary when it comes with angles? Do you guys remember that at all? Have you talked about supplementary before? Supplementary, complementary, something like that, right? Supplementary is the one that makes 180, yeah. So when these make 180, you know that these lines are parallel.
Yeah.
If they weren't 180, it'd be slightly askew, and it would end up intersecting. You can't prove that. That's why it's a postulate. But if it weren't true, and these did intersect at some point, it would really screw up math. Yeah? Yeah, we're gonna get to there. So the internal angles here are 180. These will be 180 as well. Right? Good point. So Euclid says, his fifth postulate says, if you have two lines that are parallel, that's a symbol for parallel. We use cursive lowercase letters for lines, capital print letters for points. I don't know, it's just a thing we do. If this, then the blue angle and the green angle, the two internal because they're inside, right? Same side because they're on the same side of the transversal. The two same side internal angles, or interior angles, will be supplementary. Let's use an ampersand. Not sus, but sup. These two angles, blue and green, lime and blue, are sup. Sorry. They're sup. Supplementary means added at 180. So we can use the definition of supplementary to go a little bit further. We can say therefore. Oh, I love that symbol. You like the therefore symbol? That's dope as hell. Okay? When you bust that out, you're like, oh my God, 360, 420, 69 IQ, oh my God. What this is saying is, therefore, we know that the measure, and we use an M to denote that we're talking about the measure, how much they measure, the number that they are, like 80 degrees or whatever. The measure of the green angle and the measure of the blue angle equals 180. Angles cannot equal a number. That doesn't make any sense. How do angles equal a number? How can I tell you green plus blue equals 7? That doesn't make any sense, right? That's what we'd be saying here if we weren't using measure. And so we put the little m there to say, look, we're talking about how much they measure. The number plus the number equals a number. Okay, that's acceptable, okay? So if you're gonna talk about them adding up to a number, put a little m there. Kind of pedantic. Pedantic means like you're being, I don't know. You guys know what anal retentive means? No, that was a big thing that people said in the 2000s. It was really awkward. Like, oh yeah, stop being so anal, right? You say that now, and people are like, what? It just means like you're being like, you know, your mom's just like, you got to do this, OCD or whatever. And again, it's not literal OCD, but like the colloquial version of OCD, right? Yeah, right, exactly. Colloquial means that, you know, in common speak, right? Which is funny because colloquial is not a word we use commonly, right? I love how the word colloquial means common speak, and you're like, I don't know what that means, right? It's ironic. It's just like ambiguous. Do you know what ambiguous means? Neither do I. That's what ambiguous means. It's uncertain. Ha! Okay, so this is 180 by definition, because that's what supplementary is. So we say by definition, it's 180 degrees. That's what supplementary means. You're going to use the phrase by definition a lot. How do you know that's a dog? Well, by definition, it is a dog, because the definition is it has 4 legs, it is furry, and it's a man's best friend. It fits the definition, therefore it is a dog. By definition is a reason, okay? How do we know that they have 180? Well, it's the definition of supplementary, right? That's how we defined it. Okay. What else do you know about these angles? Because what's beautiful here is that Euclid's, actually, we're not there yet. Sorry, I'm skipping ahead. So these two angles are supplementary if the lines are parallel. So if they tell us the lines are parallel, and I did by writing these little arrows here. I totally remembered to do that earlier. That's the symbol for parallel, okay? If they're parallel, then we have supplementary angles. Now, this is kind of cool because this is an A-B situation. Proposition A is if they're parallel. Proposition B is then they're supplementary. So in other words, we're saying if A, then B, or A implies B. That's a thick arrow. Dang, she thick. 3 C's, right? Dump truck back there. Anyway, so here we go. A implies B. If they're parallel, then they're supplementary. Now, what's cool about this one is this one goes both ways. It turns out the transversal, in this case, goes both ways. The transversal postulate about parallel, right? So not everything goes both ways. So for instance, I could have an A-B scenario like this. If you play dumb games, you get dumb prizes. You ever heard that one?
Yes.
Right? Now, it's not necessarily true in reverse. If I flip those around, dumb games, dumb prizes, right? If I flip those around, if you got dumb prizes, it means you played dumb games. That's not true. Not necessarily, right? Life can suck, and it has nothing to do with your choices. Sometimes it just goes that way. But if you play dumb games, you do get dumb prizes, right? That's how it works out. So that would be an example of something that doesn't go both ways. This one does. So we write it like that. Okay. If these are parallel, then they're supplementary. And if it goes both ways, then other way around is if they're supplementary, then you know these lines are parallel. So it's a way you can check to see if the lines are parallel. This is really useful. Because if lines are parallel, we get lots of free information. And that is useful, potentially, when we have a really tough problem. If I can find some parallel lines in a problem, boom, I just got tons of information. I can roll with that. And maybe that'll help me solve it. All information that we're going to use in here is going to be true information because we base ourselves off of truth as best we can. And we know it's truth because we've proven it. Or we've taken a leap of faith at some point. But we only take 5 leaps of faith in here. This is one of them. So what other information can we get from this? This is the fifth postulate, by the way. Again, it works both ways. You can call it the parallel postulate. I'm going to draw same dumb thing. What kind of a line is this? The gray line. What do we call that line? It crosses 2 others. Transversal. Transversal crosses 2 other lines. It goes across. And when we have 2 lines in a transversal, and we know those 2 lines are parallel, what does the fifth postulate say? Let's label these angles. Since these are parallel, what does the fifth postulate say? What do we know? What do we know? It's showing up. Oh, it's not. It looks black. But it's not. If the lines are parallel, what do we know about these angles? What angles do we know about and what do we know about them?
Adam.
If the lines are parallel, fifth postulate, the parallel postulate, says what about some angles? What do we know?
That some of them have to be the same.
Some of them have to be the same? That's not what the postulate says. Some of them will be the same. That's true. What does the postulate say, the fifth postulate? If they're parallel, then what? Which angles? 2 and 6? What about them? Parallel? Angles can't be parallel. Lines can be parallel. The same? They are the same, but that's not what the postulate says. Reading is hard. Words are hard.
Yeah.
Rowan? Not sus, but what? Supplementary, which means by definition, what's the definition of supplementary? Equal 180. Interchangeable, right? So, I know that 4 and angle 6 are sup. Which we know means they add up to 180, right, by definition. Or sup for short. But I told you parallel lines get us lots of information. What other information do they get? Josh, you mentioned this earlier. Oh, look at this guy. He doesn't miss. He doesn't miss. I need that on here. What's the thing? This guy doesn't miss. What's the... I need that, but I need like the clip. I need the clip. Find that clip for me while you're on there. So we know 3 and 5 are supplementary as well. Now, I can't color in 3 and 5 because I don't know if they're the same as 4 and 6 or if they're not, right? Color means they're the same when I do my drawings, right? Means they're congruent, the same angles. I know 3 and 5 add up to 180, but I don't know whether they relate to 4 or 6 or not, right? I could color these in purple and peach, but then later on I might have to go, wait a minute, 3 is the same as 6. They both need to be blue. So I don't want to do that. These are permanent. 3 and 6 are going to go together. 4 and 5 are going to go together. But the question is, how do I know that? How do I know that 3 is the same as 6? In other words, 3 is blue. How do I know? It's true. Well, looking at 3 and 6 all day is not going to get you an answer. I know that's what you're looking at. Little sleight of hand there. I can say 3 and 6, and now you're focusing on 3 and 6. They're too far apart. You need to figure out how 3 relates to 4. And you know how 4 relates to 6, don't you? How does 3 relate to 4? Oh, Rowan, sorry.
Oh, they're supplementary.
They're supplementary. 3 and 4 are supplementary. How do you know it's supplementary? Someone else other than Rowan. Explain how they know. You have a stack of books over here, and Adam's hand is like... How do you know 3 and 4 are supplementary? In other words, they add to 180. How do you know? Motown Wrecking Crew? When I first saw it, I didn't see the Motown part.
Oh, yeah, I hope so.
Gotcha. Motown Wrecking Crew is a reference to the historical Wrecking Crew. It was a band, right? They were in a studio, and so people would come in and they'd be singers for Motown in Detroit, and they need a band to back them up. And so for every record, this Wrecking Crew is what they called them, would play the instruments on it, and it created some of the best records of all time. But that's cool too. That's what they're referencing. It has to add up to 180 with number 4, so it's blue. Maddie's right. How do we know these are supplementary? Well, we already know 4 and 6 are supplementary, right? And we know 3 and 4 are supplementary, but how do we know 3 and 4 are supplementary? Yeah.
Because they're on a straight line.
They're on a line! So, this is great. Parker Foreign, geometry is the only class where most of my answers I get with, like, miming. Like, what are the lines doing? I don't remember what it's called, right? They're doing this. Or, he did this. 3 and 4. It took him like 15 minutes to figure out what he was talking about. I wouldn't let him say it. They're on a line. How do we know a line is 180? Well, here's a line. How do I know that the angle between 2 points on a line is 180?
Magic.
Nope. It's kind of a definition, actually. We define it to be 180. But the real reason is because of Call of Duty. Right? It's half a circle. 360 no scope, Snoop Dogg, aim assist, right? So, it's 180. Which means this is 180 altogether, yeah? If this is 180 altogether, another way of saying that is they're supplementary. So 3 and 4 are supplementary because they're on a line. We call them, when they're on a line, a linear pair. And that's when you've got 2 angles that make up a line. Like this angle and this angle. They're a linear pair. Pair, meaning 2, not the body shape, but linear meaning line. If something is linear, it means it's line-like. Like line. So a linear pair is a pair of angles that make up a line. That's what 3 and 4 are. Linear pair theorem, LPT for short, says that they must add up to 180. It must be supplementary. We'll talk about that later. So, by linear pair theorem, LPT, we know that angle 3, which will remain colorless, and angle 4 are supplementary. Correct. They're a linear pair, so they're supplementary. Wait a minute. If 4 and 6 are supplementary, what does it mean to be supplementary? What does it mean? They equal 180. What does it mean to be supplementary? They equal 180. So you're telling me 4 and 6 and 3 and 4 add up to 180. Well, if they both add up to 180, don't they equal each other? They do up to 360, that's true. But they equal each other. So you're telling me the measure of angle 4 and the measure of angle 6 is going to equal the measure of angle 3 plus the measure of angle 4. Oh, I could have done angle 3. Darn. Almost was efficient. Therefore, this is true. If they both equal 180, then they equal each other. We call that a substitution by subs. Substitution is a switch out, right? Like when a sub comes in here. Now, it's important for subs to be exactly the same for what they're switching out for. 4 and 6 are the same thing as 180 when they're put together, right? So whenever I see 4 plus 6, I can switch it out for 180. Well, I know 3 and 4 equals 180, right? So instead of saying 3 and 4 equals 180, I can say 3 and 4 equals this. Because 180 and 4 and 6 are the same thing. They're the same idea. Much like a substitute comes in and they're literally me, right? They walk in, they might as well be me. We're so similar. I could be a sub right now. You wouldn't even know. All right, so we switched out 180 for these two because they're one and the same, right? These are 180. Now by algebra, if I have 5 equals 5, true statement, yeah? We agree? No argument today? Okay. What if I subtract 3 from both sides? I get 2 equals 2. I am not a crook. 5 equals 5, true statement. 2 equals 2, true statement. After we subtract the same amount from both sides, it'll still be true, right? That's algebra. After I subtract the same amount from both sides, I get this statement. And again, as long as I do it to both sides, it'll still be true. It'll be a different statement. 5 equals 5 is different than 2 equals 2. After I subtract angle 4 from both sides, what does my statement say? 3 is 6, right? Angle 3. The measure of angle 3 equals the measure of angle 6. I'm just going to write angle 3 is congruent to angle 6. Ideas are congruent. That's that symbol. Measures are equal. Numbers can be equal. Ideas are congruent, okay? So now I know 3 and 6 are the same. Let me break it down. So we said linear pair means these are supplementary. And we know from earlier, by the fifth postulate, that these are supplementary, right? Well, if these are supplementary, and these are supplementary, see how they overlapped 4? This one has 4 in it, this one has 4 in it. Subtract the 4 from both sides. What's left over must be equal. In other words, if green and blue always go together to make 180, pretend this is 140. If green is 140, what's blue? 40. Well, if green and blue is 140 and 40 to make 180, and I know this makes 180 and that's 140, if this is 140, what does this have to be? It has to be 40, right? It'll be the same as this. Has to be. There's only one way to make 180 if you've got 140. You have to add 40 to it. Only one way to make 180 if you've got 140. You have to add 40 to it. These will be the same. That's what we're saying here. This is a linear pair, so they're supplementary. These are supplementary because of the fifth postulate, right? And if they're both supplementary, they're both 180, which means they equal each other. Subtract the middleman. What's left over is true. Let's take a break for a second. It has to add up to 180 with number 4, so it's blue. Correct. What else do you know? What else do you know on this diagram? Josh said earlier that 3 and 5 are supplementary, right? So if 3 and 5 are supplementary, what color must 5 be? Has to be. Can anybody explain why it has to be green?
Because 6 is blue and it's on a straight line.
Mm-hmm. 6 and 5 are a linear pair, right? So they're supplementary. And these had to be supplementary because of the fifth postulate, right? So if this equals 180 and that equals 180, subtract the common. What's left must equal itself, right? This is 180. Let me do that again. This is 180 and this is 180. 5 and 6, 6 and 4. Subtract the thing in common. What's left over must be equal. Now that's the same thing we did here, right? Just with different numbers. So what we're going to do is, instead of writing that all again, we're going to say by the same or similar logic. I usually say same dumb logic because I'm a rebel. By same dumb logic, same idea, I know that 5 and 4 must be congruent. Cuts to the chase a bit. These are 180, these are 180. Subtract what's in the middle, what's left over is the same. Same dumb logic. Fifth postulate, linear pair, 180 for both. Subtract, they're equal. How do you feel about the internal angles? Because we've covered the internal ones, we now got to cover the external. How do you feel about the internal? Feeling okay? Feel good. You know, let's play Team Fortress 2 ever? The Scout? No? Okay. All right.
Wow.
All right, so what else do you know? Time to talk about 1, 2, 7, and 8. What do you know? What do you think? What do you conjecture? Remember, conjecture is just a guess. What does it look like? What do you think? Go ahead, Rowan.
1 and 7 and 2 and 8 are supplementary.
1 and 7 and 2 and 8 are supplementary. Cool. That doesn't get me any colors, but it does tell me they're supplementary. So 1 and 7 should equal 3 and 5, right? Or 5 and 6, or 4 and 6, right? That's true. I'm going to ask a more specific question. What do you know color-wise? Which ones match? And how can we figure that out? Remember, we're going to get a lot of true information here, but not everything's going to be useful. Okay. What do you think? Make a guess, and let's see if we can prove it.
Adam!
I think 1 is green.
You think 1 is green?
Yeah.
He right! How do we know 1 is green? Can anybody explain why 1 must be green? I'll give you a hint. I don't normally do hints, but I'll give you a hint.
Adam!
Like, you don't do blue on top of it. You want to have flips.
You want to have them.
Wait, no. You're like, yeah. They flip it, and green will be on top of it.
That's true, but why is that? Because you noticed a pattern. But why is that pattern true? How do we know that pattern is true? Because when I was in kindergarten, they'd say, circle, square, circle, square. And they say, what's next? And everybody would say?
Triangle.
They'd all say square, but I would say triangle because I was like, wait a minute, maybe that's not the whole pattern. Maybe it just happens to do the first two back to back and then it does something different the next time. We don't know that. I was right. How do we know that the pattern of crisscross applesauce always works? Parallel means the lines don't touch. Angles have nothing to do with parallel. Oh, hold on. What are you saying?
That angle would also be 180.
Okay, don't use that angle. I'm all about pronouns. However, I do need to know what you're talking about.
1.
1 is?
180.
Ooh, we don't know that. 180 makes a line.
Yeah.
1 alone does not make a line.
T is a line up.
This is true.
So T going through would that angle be 180.
What angle? What angle?
L.
L is a line.
Yeah. I don't know. Yeah.
The angle.
So what?
Angle 1 is 180? Does that look like 180 to you?
Oh no.
You're onto something. What is 180? Adam!
What is 180?
I don't know. Tell me what you're going to say.
Oh, I was going to say that. What was I going to say? Oh, angle 1 and angle 4 have the same distance.
Distance?
What?
It's that X right there.
So B-Day kids, you didn't have to do this for Wednesday, but A-Day kids did. They had to prove something called vertical angles theorem. That's what's on the board right here. You'll have to do it for next week. That's okay. It's Scissor Theorem, right? Something. Your words, not mine. Right? The idea being that when you have an X or a pair of scissors, right? Alex Anderson came up with that. Something's going to be something, Scissor Theorem, so they're the same. Okay, so this angle right here, how do we know it's the same as the bottom angle? It's a theorem. We're allowed to prove it, right? Vertical angles theorem is a theorem, so we should be able to prove it, right? So pretend, I know this didn't happen. So imagine that you forgot that vertical angles theorem existed. Imagine that you forgot. That's going to be hard since you all remember that instantly. Try. Okay, so you forgot what vertical angles theorem is. So you have to prove it. Because you forgot what to call it. You have to just go through the whole thing, right? Theorems are nice because they cut to the chase. But they're provable, so you can figure it out. You can BS your way to it. So how do I prove this is the same as that? Because that's basically what we need to do, right? What do you notice about the red angle and the green angle? Joshua, they make 180.
Yes.
How do I know they make 180? It's a straight line, right? So they're a linear pair is what we call it, right? A pair of angles that make a line is a linear pair. Linear pair means they're supplementary, right? Linear pair theorem says they're supplementary. Supplementary means by what? By definition, they add up to 180, right? So that adds up to 180. What do you know? And I don't have good colors. Oh, we can use black. Okay. What do you know about green and black? Also, by same dumb logic, they add up to 180. So if green and red add to 180 because of linear pair theorem, and we also know that green and black add to 180. Therefore, green plus black equals green plus red, right? You did? And why does that tell us that black and red are the same? I love when I ask the same question twice. Right?
Algebra.
Because algebra. What are we doing for algebra? What are we doing?
Subtracting the green from both sides.
If we subtract the same from both sides, it's still a true statement. Check this out. Josh. 5 plus 5, true or false? Or 5 equals 5, true or false? True, thank you. After I subtract 3 from both sides, I get 2 equals 2. I'm not a crook. Is 2 equal 2 true?
Yes.
So we were true before, we're true after.
Yes.
Is 5 equal 5 the same statement as 2 equals 2?
Yes.
No.
They're not the same, but they are both true, right?
Yes.
So I can go from something that's true, and as long as I subtract the same amount to both sides, it'll still be true. Different statement, but still true.
Yeah.
True statement, right? This equals 180, that equals 180, so they equal each other. If I subtract the same from both sides, what's left over also must be true. And what do I get? Black equals red, and I've proven vertical angles theorem. This is VAT, vertical angles theorem, or scissor theorem. You hate what? Oh, okay. For next, wait, for this week, all I need is proof of vertical angles theorem, which is what I just did, basically. Support your reasoning. I did a rough outline, Mika. And then I also need either addition, subtraction, multiplication, your choice. And then I also need the segment addition postulate. Remember, it was the square, the rectangle, and then the weird shape. I need the first two thoroughly examined and explained, and then the weird shape, I need your best effort, okay? It's all on Google Classroom, the picture of that and everything, and what I had written on the board. Good question, Mika. All right, so how do I know that one is green? Somebody explain to me.
Vertical angles theorem.
Vertical angles theorem. If I forgot vertical angles theorem, or I said, hey, I want you to prove vertical angles theorem, imagine I asked you to do that, right? For next week on your portfolio, or for 8A people that I asked you to do it Wednesday. Imagine I did that. How would you prove that 1 and 4 are the same without using vertical angles? What do you know about 3 and 4? 180. You guys just like saying words. 180 because they're linear pair. What do you know about 1 and 3? Linear pair, so they add to 180. So 3 plus 4 equals 180, and 1 plus 3 equals 180. What's the common, man? 3 and 4, 1 and 3, what's the common? 3. So we subtract 3 from both sides, and what's left over must be the same.
And 2 would be the same.
2 is the same idea, right? Same dumb logic, or you could say vertical angles theorem, right? 7 and 8 are vertical?
No.
You mean 5 and 8, right?
Yeah.
And 6 and 7?
Yeah.
So we get all that for free just because the lines are parallel. Because that's all I said, right? Lines are parallel, and boom, look what all I got. That's useful. Now your job is to answer this problem, right? There's always a where are your gods now problem. What am I going to draw next? Ooh, I am. And they're actually going to be called what? What kind of lines are these? Transversal. Something, something, say its name. All right, so right, so here we are. And I'm going to tell you that these are parallel, actually. P and N are parallel. I didn't use O because O looks like zeros. I'm going to tell you that M and L are also parallel. Now, if I just use one arrow, it looks like these are parallel, and that ain't it, right? So I'm going to use two little arrows. So we say P is parallel to N, and L is parallel to M. Neither of the two shall cross, right? P and M aren't parallel, obviously, right? And if that's true, what do you know about these angles? And how many angles do we have? Twice as many as we had before, right?
Yeah.
What do you know about these angles? If these are parallel, what do we know? First of all, the postulate. Euclid's fifth postulate, the parallel postulate. If the lines are parallel, then what? Let me cover this up, because you know how to solve this problem, right? We just did it. Two parallel lines, one transversal. Euclid's fifth postulate says what? Josh mentioned it earlier. The fifth postulate, again, we can't prove it, it's a postulate, but what does it say about parallel lines? They always produce what?
180.
180, where? Which angles are going to be 180? 4 and 6. The same side interior angles will be supplementary, yeah?
And then same for 12 and 14.
So this and this is going to be the same. So we know by the fifth postulate, or by the parallel postulate, I'm going to write this, by parallel postulate, he said, I was teaching kindergarten once, and this kid gets up, we're in circle time, right? We're sitting, and he stands up and he points at this other kid and he yells at the middle class, he said doo-doo turd! The kid did not. But the other kid that he pointed at stands up and points at him and he said, he just said doo-doo turd! And then everybody in the class stands up, they said doo-doo turd! They said doo-doo! And it was just complete chaos. We were having a good time, we were reading a story, and then all of a sudden this happened. And everyone said doo-doo turd. And apparently this is like the worst word ever. I don't know, reminded me of something. Anyway, 6 and 4 supplementary. Good thing we're all more mature than my kindergartners. I love that story. It was just absolute chaos. We were having a good time, everything was normal, and then all of a sudden the accusations started flying. I mean, it was Among Us, but like 10 years early. Our sup, not sus.
I don't know, man. That kid seems kind of sus. To
He
me.
said doo-doo turd. He said doo-doo turd.
I saw him then.
I saw them use doo-doo turd.
Exactly.
remember
I
this one
kicked
time.
out a game immediately.
This is from the fifth postulate, or the parallel postulate, whatever you want to call it.
I made red.
Okay? If we can be mature, we'll call it by its real name, PP. Okay?
PP.
Parallel postulate, these two are supplementary. What else does that imply? 3 and 5 are supplementary as well?
Yes.
That's good, but what about their relationship to 4 and 6? Because I want to color them in. 5 is green because why? Who can tell me why 5 must be green?
And then 3 5 is green because
Yeah?
Because the vertical angles theorem for the
5 and 8 are vertical, but you don't know anything about 8.
no, like how 5 is green.
Yeah, but we don't know 5 is green yet. I'm asking why is 5 green?
Oh, because
5 and 6 together make 180.
4 and 6 are supplementary, right? And we know 5 and 6 are supplementary. How do I know 5 and 6 are supplementary? I know 4 and 6 are because of PP, right? Parallel postulate. That's Euclid. How do I know 5 and 6 are supplementary? How do I know that? They're a linear pair, right?
Yes.
Angle 5 and angle 6 are a linear pair. In other words, let's cut to the chase. Are sup because by linear pair theorem, right? LPT. Linear pair theorem says linear pairs add up to 180. They're supplementary. So if 6 and 4 are sup and 5 and 6 are sup, what does that tell you? They both add to 180, right?
Yeah.
And if they both add to 180, then what's true about this and this?
4 and 5 are equal.
They're the same. They're equal.
Yep, the measure of them is going to be the same. Right? Remember, measures are equal, but ideas are congruent. So angle 5 and angle 6. Oops, sorry, I don't know angle 5 is green yet. My bad. We're going to prove that it's green. Angle 5, which will be green eventually. Angle 6 and angle 4. Therefore, you love the therefore symbol? I love that therefore symbol. Therefore what? 5 and 4 are congruent, so I can use green now. No cap. No cap. What else do you know? What?
3, 6.
3 and 6. What about them?
They are.
3 is blue.
Yes.
How do you know 3 and 6 are the same?
4 and 5 are the same.
4 and 6, same thing. Now I'm gonna write same dumb logic, but obviously we need to say it again because you guys are just like, oh, because it is, right?
It's.
4 and 6 are sup because of PP, right?
And then 3 and 5.
6 are.
3 and 4 are sup because of LPT, right? So if these are sup and these are sup, subtract the middleman. What's the middleman? 4. What's left over must be the same. So we're going to say by same dumb logic or by similar logic. I use same dumb logic because I'm a rebel. I know that 3 and 6 are congruent. Again, ideas are congruent. Measures are equal. That's the internal angles. How do I know 1 is green? Give me 2 reasons. 1 reason. Everybody's favorite, right? This guy.
That.
Vertical angles theorem.
Your words, not mine.
Scissor theorem. So, what is another reason why 1 has to be green? You know in math class.
I was just taking it now.
I love how I just looked at everybody and they're like, oh, I'm so sorry. I used to do it as a band director. I'd yell at the drummer, or I'd yell at the trumpet right in front of the drummer, and he'd think I was yelling at him. You! You need to play your notes right. You're missing a B flat, and the drummer would just go, oh, okay. And you, trombone player, right? Drive them nuts. 1 and 4 are the same because of vertical angles, but also we can prove that by another way. Hi, Maddie. 3 and 4 are supplementary because why? LPT, linear pair theorem. 1, which we don't know is green yet. 1 and 3 are linear pair because, or 180 because they're linear pair as well, right? So if this is sup and this is sup, common is 3. What's left over must be the same. We get this and we get this. Now for you guys, the question you want to ask is, are these guys connected over here or are they their own thing? Because you're going to get the same thing, right? Like these are going to match, 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 right? And vice versa, right? Same as over here. But do we have to use different colors? Does it have to be like purple and orange for all these? Because they're not equal to this. Or are we going to use blue and green over here again?
Yes.
Why? That's your conjecture. Why?
Because they're the same measurement.
Because, okay, P and M are parallel to each other, so therefore, I don't know which side it would be, but 11 and 13.
Check it out, check it out. This guy's right. This guy's right. Excellent job. Nice job, guys. We have 2 parallels and a transversal, and we get matches, right?
Yes.
2 parallels and a transversal, so we get matches. I want you to do the rest of these and explain why Go back and watch the video. It's going to take some time to be concise. You're going to write a book trying to say what I said in a paragraph. That's what's going to happen. Okay, I'm used to being concise when it comes to writing. I'm not very good when it comes to talking. I want you to check this out and write me a post for next week about this. Explain how they're connected and how you know. You're going to have to prove vertical angles theorem because you're B-Day. You need to do that for next Wednesday. Okay? And the other two things that I needed from this week. Get on that. I'm not doing these stay on Friday from 3 o'clock to 5 o'clock because you bozos couldn't show up on a Wednesday. And I know you all had good reasons. I don't mean to say you didn't. I assume you all had good reasons. The Lord knows you didn't, but I assume you did. Right? For those of you that didn't meet with me last time and still haven't met with me, I'm not doing late Fridays anymore because I can't. I got other stuff I got to do. I'm growing up. I can't stay after school and hang out all the time. I figure all day Wednesday should be good enough. And if it isn't, we'll have to wait a week. You know, just deal with the grade. Because again, I don't care about the grades. And if you don't care, then it makes two of us. Figure out the rest of this. Can you do it? Don't wait to do it. Rest of the time's yours. You want to draw it, start writing. If you're going to record this in bulb, don't write this. Oh my god, trying to put an angle symbol in there and then like plus signs and measure and then like therefore, oh my god, no. Write it out, take a picture. Exactly. You can still type and talk about stuff. That's good, but like if you're doing this and you're trying to figure out how to do a parallel symbol, good lord, just take a picture, okay? See you later. Hey Mitchell. Bye. Fourth hour.
The one with Snoop Dogg.
Email it to me. Send that to me. Send it to me. Thanks, Josh.
Yeah.
All right, everybody but Cliff today, looks like, for last hour.
See you, Mr. Mack.
Bye. Have a good weekend. Stay safe.
I'm meeting with you Friday, today. I have to come back on.
Oh, right. It's going to be everybody meeting with me online, but we'll figure it out.
Okay.
Bye.
Bye.
Gage, just run him over, okay? He's a good kid, but sometimes just takes a lesson, you know? Talking about the fifth postulate today, everybody's favorite postulate. Get psyched. Jamie. Gage, when are you be ready to show me that portfolio stuff that I needed?
Well, that's a valid point, though.
Monday? Yeah. Can you do that? You know what you need to do? Yeah. There's a thing on Classroom. I wrote it all on the board. You know what I'm talking about? Yeah. For real? Yeah. Okay. I'll take it. All right.
Have you had English yet?
No.
Do you like that Susie?
Fifth postulate, baby. Everybody's favorite. The first four, boring. We don't need a seventh, luckily. Remember, the more postulates you have, the less stable your geometry is, because it's all leaps of faith. Euclid wanted it to be 4 for a long time. He was like, I don't want to admit that I can't prove this last one, but eventually he had to cave in. Turns out if it weren't true, it leads to like a whole bunch of crazy stuff, and we'll talk about that. But like, yeah. Like space-time, man. Space-time.
Space-time continuum?
Yeah.
When you walk by a guy you talk to a date and then take one of these. Yeah. Say hi to Anne. Hi, Anne. I'm sure you can hear me, but hi. Oh, my hair looks like it. Your hair? Oh, God, Jamie. Oh, my God. I was gonna wake up and scream this morning, but I was so tired. I got out of bed at 6:50. I do not need it. I got up at like. Not doing it next year. I got up at like 7 something today. Guys, I'm the teacher today. We're going to be talking about mythology in Cersei.
What are you doing?
I was the teacher.
What are you doing?
The teacher!
I remember Thomas Schlaffer writing, we had to do portfolios last year, but they weren't nearly as what they are this year. Just kind of like, instead of a final, we just did it. and he had to explain the topic, right? Like teach it, part of the portfolio. And he began his teaching topic with, "Now I am the teacher," blah blah blah, and just was really obnoxious. And I stapled that or nailed that to my wall.
Is it a poem?
I'm pretty sure it's Miss Richardson.
Oh.
Sorry, Miss Richardson. But there it will stay. Also where I got this guy.
What guy? Oh, that makes sense.
Oh
I said
my
hi
God,
to
why
Anne
is my
Marie.
Hey,
face
kid.
like this?
Why does your what look like this?
Her hair.
Oh, sorry, it
Is
happens.
Cynthia no longer in this class? Because I heard she's got her schedule.
I have no, I don't know things, guys. No, she's not on the attendance.
Oh!
Here, listen to listen.
Today will be chicken strips, mashed potatoes,
Maddie's here, Mitchell's here, Logan's here, Jordan is here, Olivia, Ann, hey Troy, Isaiah, Cooper. No Zach though.
Resting is with you for second and third shift CNAs. If you are interested, please stop in the office for more information.
Jordan's online.
If you are driving, or do not have a
No Gina yet. Jamie's here, Gage is here, Andrew's here. I see you, Cooper. Emery, Olivia, no Lexi today. So only missing Gina and Zach right now.
Oh, that's easy.
Like I'm trying to see like a photo.
We're always one decision away from living a totally different life. Have a great weekend, Marissa.
I didn't really think that as messy as you might want it, but I don't know.
All right, today we're talking about the fifth postulate, which of course is everybody's favorite postulate.
Mine's the fourth, actually.
There are only 4 postulates originally in Euclid's writings, and he was so hesitant to add a fifth, because again, more leaps of faith. Oh yeah. Oh wait, did we spray? Did I not spray?
No, but my desk is just sticky for some reason.
Yeah, I don't have a lot of kids last hour. Can I spray, guys? I'm really sorry about that.
That means I have to get up again.
Yeah,
It's
that's right.
not your fault, it's desk.
I'll get you one.
Alright.
I got you, bro.
Oh, come on.
How did you not know?
I better not have bleach.
Is that really my fault? Like, is it?
No.
Because I feel like.
Could have pointed that
I
better.
feel like. Well, I don't have great aim. You know what I mean? Who do we blame, right? I mean, come on. Shame on me, shame on you. Something, something. I don't know.
Mr. Mack, how much do you know about mythology?
What?
How much do you know about mythology?
I know a pretty good amount. Why?
Do you know Circe?
No. I know the concept. I think like the idea. I've heard of Circe, but I don't know.
Well, we're reading the Odyssey.
Right.
We got to the point
Yeah.
where Circe threatened to cut off Odysseus' dick.
Nice.
Oh yeah.
It's funny.
Amazing.
I know. She said she wanted to. She said she was gonna make him a weakling.
Oh, gotcha. Well,
it's, you know.
just like Samson. All right. So, the fifth postulate. First 4 are kind of boring. They're kind of obvious, like segment addition postulate, right? You can take 2 segments, put them together. Now they make a bigger segment. That's the same length as the 2 put together. Another postulate, the second one is 2 dots make a line. Not very exciting. Euclid only had 4 postulates, and they were very, very basic, and he made like an entire book out of it. And he, for the longest time, was hesitant to say there was a 5th postulate. He's like, I know there's this thing. It has to be true. I can't prove it. But I don't want to use it to prove anything else because I haven't proven this already. And I only want 4 postulates because 4 leaps of faith, that's pretty good, right? To build an entire realm of mathematics out of it.
Yeah.
Subtraction. If I can keep it to 4, that'd be better. But eventually he caved in. And this is what he caved in on. We talked about this a little bit yesterday. It's called the parallel postulate. Again, you can call it the 5th postulate. But it has to do with parallel lines. In parallel lines, the idea is that they never touch. And the problem is that lines go on forever. And how do you prove they don't touch, right? And he couldn't prove it. So what he said is, here's my postulate. We have two lines. Let's call them L and M. If I draw another line that cuts them, we call that line T for transversal. Transversal means to go across. So see how it goes across two other lines? Now, technically, any two lines that aren't parallel are going to cross, right? So you call any two lines transversal as long as they're not parallel. But that's not very useful, because now like everything's basically a transversal. Only ones that wouldn't be are like these guys, right? Any two lines I draw would be a transversal unless I draw them very specifically. And so that's not a very useful term, right? So what they did is they said, look. Transversal, we're going to leave that only when it crosses two or more lines. So technically L would be a transversal because it crosses this guy. But that's not interesting because then everything's a transversal. We're going to say it has to cross at least two lines, okay? At least two. So the only transversal here is line T. So Euclid says, if I have two lines and we draw a transversal through them, and the internal angles, the same side interior angles, these two right here, are supplementary, then those two lines are parallel. They'll never touch. Now that's quite a mouthful. Let me write this out. Basically saying, if the green angle and the blue angle are supplementary. What does it mean to be supplementary?
I don't know.
That's okay. Supplementary means they add up to 180. Remember like complementary, supplementary, you might have talked about those, right? Again, 180 happens so often that they were like tired of saying the phrase, they add up to 180. So they just said they're supplementary, right? So we're gonna use sup for short, not sus, but sup. Lime and blue are sup. Lime is always sus. Lime is always sus.
What about white?
I play white. I play white. Chef hat or the crown?
I have the horns.
Traitor. All right.
I'm sorry.
Lime and blue are sup. So they're gonna add to 180. If they added to 180, Euclid says, then L is parallel to M. Again, we can't prove this. This is a postulate, right? How do we prove that they never intersect? But the idea is if we have a line, like if I draw a line straight up through here, right? It's like 90 and 90. 90 and 90 adds to 180. And that measurement's the same here and here, then the lines must not be getting closer together. And if they're not getting closer together and they're not getting farther apart, then they must never touch. Now, Euclid says you don't have to just measure straight up like we talked about yesterday, right? I can tell my hands are both the same size if I put them up against each other, right? But I can also tell they're the same size if I measure them like this. Check this out. If I turn them the same angle, it's still pretty obvious they're the same size, right? So Euclid says they don't have to just be straight up next to each other. They can be at the same angle, whatever the same angle is. And that same angle is going to create 180 degrees between the ceiling and the floor. Okay. Again, if I don't have them turn the same way, then obviously they're not going to be parallel, right? And that measurement's not going to be accurate. You ever heard the statement, if you play dumb games, you get dumb prizes?
Yeah.
You should have heard it because I said it yesterday.
Yeah.
This is an A-B relationship.
See your way out.
Yeah, I know. I was waiting for somebody to say that. So the idea here is this. If A, then B. Or in other words, A implies, symbol for implies in mathematics is this big thick arrow, she dummy thick, dump truck, 3 C's. A implies B. Now, not everything goes both ways, although we are accepting when it does. A implies B means that if this, then that. So for instance, if you play dumb games, you get dumb prizes, right? A implies B. Now, the reverse isn't always true. We like when it is, but it isn't always. So for instance, dumb games, dumb prizes, right? Flip those around. If you get dumb prizes, you must have been playing dumb games. That's not always true, right? Life sometimes just sucks, and it's really no one's fault, right? So not always does it go both ways. That's a statement that doesn't go both ways. This statement, though, the postulate, the fifth postulate, does go both ways. So we use this symbol. It's true both ways. So you can say, if these are supplementary, if these add to 180, then these are parallel. You dig? If these are parallel, you can say it the other way around. If these are parallel, then you automatically know these are 180. Now this is really helpful because when we have parallel lines, we get a lot more information than this. I'll show you that in a second, okay? And why do we like more information? Because sometimes we have really difficult problems, and if we can get a lot of information about it, we might be able to solve it, right? So just from these being parallel, this is the symbol that we use for parallel, by the way. Big thick arrow, again, dummy thick and all that, right? Then we know these are supplementary, and vice versa. If these are supplementary, then these are parallel. That's the fifth postulate. We call it the parallel postulate, or PP for short. If you're mature enough to call it by its real name, parallel postulate, you're allowed to call it PP, okay? As long as we're all being mature, right? It reminds me of a time when I was teaching in kindergarten. Hi, Gina! And we were all having circle time, right? The kindergartners sitting on the rug, and we were talking about a story or whatever, talking about world peace or something. And one of the kids stands up. All of a sudden, we're talking about world peace. He stands up and he points to some other kid and he says, "He said doo-doo turd!" And the kid didn't. I mean, it was quiet. What's going on? But before I know it, the other kid that was being pointed at, stands up and points back at him and he said, "He said doo-doo turd!" And then all the other kids get up and they point at those kids. "They said doo-doo turd!" And then he said. The entire room just breaks out in chaos. I mean, just like that. Like, there was nothing. And then all of a sudden one kid's like, "I'm just going to see what happens." Right? The Joker. Here we go. Right?
I live in a great kindergarten.
I mean, it was like Among Us, but like 10 years early. You know what I mean?
Oh, no!
He says, no, I saw him, right? So anyway, if we're mature enough to handle doo-doo turd, which apparently is the worst word you can say, like, "Oh my God, did you hear him?" Right? Kindergartners are the best. Then you can call it parallel postulate, PP, okay? So the parallel postulate says, and again, it's a postulate, leap of faith, can't prove it. Yes. Yes, yeah, mark it. No, it's cool, it's cool. So L and M are parallel. That means these are supplementary. If these are supplementary, L and M are parallel, both ways. Cool, got it, excellent, you got it, you totally do. I'm not gonna ask the same question again in like 5 seconds, and you won't know it, because you know this stuff, right? You totally do. You totally do.
No one cares wearing red, Mitchell.
Mitchell, I miss you, I hope you're feeling better.
Mental sucks.
Oh, that reminds me. Today's the last day we're going to be using YouTube. We're going to switch over to Google Meets. The reason we weren't using it before is because Google Meets sucked and they had to develop it a lot more. It still kind of sucks a little bit, but it's at least usable now. Also, we were using Zoom last year and that really sucked. I wasn't a fan of that. So I used other things. I used Twitch, etc. And now I use YouTube because Twitch is blocked. We can go to Google Meets now. Google Meets no longer has to have me send out a link every single time we want to meet together, right? You can go to Google Classroom and just click it. That is a game changer for me. The stream is not going to be delayed at all, like YouTube is a little bit. Although the quality of the picture and the sound will be a little bit worse. But they've improved it enough to where it can compete. Also, I can do the little me down here and picture up there now. There's a way to do that. And I got a way where it automatically sends it to YouTube afterwards, so you can watch it later, or if you missed it, right? So all of that is available now. So I think I'm going to switch over to that, okay? So this will be the last week. I'll send you links. We'll get it set up in Classroom. That's what we'll be running next week, okay?
Now, when we have questions, we can ask in real time.
Exactly. In theory, right? I'm not going to make you participate. Like, Lord knows, okay? I want to roll out the red carpet for you guys just for showing up and saying you're here. I know half you guys are dipping, right? But the fact is you show up, right? And I think we should be thankful just for that. If I make it difficult, right, because I'm going to, keep track or whatever, then you guys might not show up at all because you're like, I might have to talk or show my face, and then you're really not learning, right? I don't want to make it more difficult. The kids that are going to show up and stay are going to show up and stay whether I'm taking attendance or not. And the kids that are going to leave might stay if I'm not making them show their faces, That's my logic. And if I care about learning and not about control, power struggle, then that's the choice I'm going to make. So anyway, I won't, even though we're going to meets, I'm not going to be like, okay, now, you do you. You do you. You don't have to participate. But if you wanted to, you could, in theory, talk out of my speakers to the rest of the class. And they could hear you on the mics. I want to get a mic for every desk, but we'll see.
That would be terrible.
I can just get cheap ones with a little button. What is the capital of Arabia? Right? I don't know. Right?
Presidential debate.
You know what I mean? Yeah, exactly. You're on mute.
Okay.
Anyway, we're not going to get into that. So, remember that thing that I told you wouldn't forget?
White is not
do you see how I just distracted you with that story that you thought was just off the cuff, the thing about YouTube? And it seems like I'm just being goofy. I did that for a reason, because if I distract you, I can ask the same question twice and really see if you know what you're talking about. That's a teaching technique I invented. I never went to teacher school. At least not for math. Anyway,
What'd you go for?
music.
Oh. Why did you become a music teacher?
I did become a music teacher.
Did you not like it? Or?
No, long story. They didn't have funding for music, and they said, but you can teach math, right? And I was like, of course. I sucked at math. But you got to make money, right? And then I was good at it. Because I think about why stuff works and what it means and not just memorize the steps. It worked for a lot of kids, especially the kids that normally struggle. I was like, you know what? I'll do that. I just like teaching.
Here you are.
Here I am.
How many years later? Who knows?
Time is an illusion. All right, so here's 8 angles created by, what I'm going to tell you is 2 parallel lines. Right now, you don't know they're parallel? Even though they look like it. Remember, looks can be deceiving, something.
It is, it's just a drawing.
Right. You can't assume anything. Trust no one. But now you can say they're parallel. So let's call it L and M. I use L because it's line, right? L, line. I use cursive lowercase because that's typically what we do. Regular letters are used for like points, like point A, point B. So we say line L is parallel to line M, and we'll call that transversal T. I always call my transversals T. All right, so if these two are parallel, what do we know about the angles?
They should all equal 180.
They should all equal 180.
No. They're matches on the other line.
Ooh, I like it. They're pair, perhaps, right?
Pair, yeah, thank you.
Okay, no, that's cool, that's cool. No. We create language, guys. Just because it's like, oh, that's the wrong term. Dude, it's only the wrong term because somebody else thought of a different one, right? As long as you know what you're talking about and I can understand what you're saying, that's language, right? So, give me some pairs of angles that would be 180.
No, hold on, wait. 4 and 6.
4 and 6 are going to be 180? That's true. Why are they a pair?
Because they're both inside angles, but they're...
Gotcha. You're thinking something different than me, but you're absolutely right. So, what she's remembering is that the PP postulate, right? Or that's redundant. That's the parallel postulate. The parallel postulate by Euclid says if they're parallel, then the inside angles on the same side will be what? 180. What's another word for saying they equal 180? Not sus, but sup. Exactly.
I could remember.
So these are sup. I know, you're going to remember sus, and you're not going to remember sup. Both green sus. So, because of this, so since, let's write this, since, you're going to have to do this as a post for next Wednesday. Since these are parallel, I know that 4 and 6 are supplementary. So I'm going to write that. That's by the parallel postulate, so by PP. So I'll write that in a second. I forgot to write a 6. Angle 4 and angle 6.
And then...
By PP. Parallel
Isn't
postulate.
also 6 and 3?
Something about them?
Yeah. No. Wait. No, hold on.
What's your conjecture? Maybe you don't know why, but what's your conjecture? What do you think about 6 and 3?
I was thinking that they would also equal 180, but then I'm looking at the angles, I realized that they're both the...
It looks like they wouldn't. Now, looks can be deceiving, but usually when we make conjectures, it's like, well, that looks like it should be the same.
I know,
Let's see if it can be.
I remember that they're both the bigger angle of their
Right, yeah.
side-by-side pair.
Uh-huh.
So never mind.
So what about 3 and 4? What do you know about them?
They should be 180.
Why?
Because they're on the line, and it doesn't matter how many times they're second, they should always be
So,
180.
I love how in geometry class, and you're using words, which is great. Words are hard. Parker Porn asked, like, why are these 180? And he just goes like this.
Fine.
And no one in class knew what he meant. I refused to let him talk. I was like, just do this and have kids figure it out. And they could not figure out what he was saying. But you're right. He was saying they're on a line. Now, why do we know that they're 180 if they're on a line? Well, check this out. Here's a line. I'm going to pick 2 points on this line. This one and this one. The angle between them. Why do we say that this is 180? How do we know? You guys play Call of Duty?
No.
360 no scope, aim assist, right? We know a full circle is 360, right? 420 Snoop Dogg. So if a full circle is 360, a line is obviously half circle, right? Okay. So we call those two angles that are a pair a linear pair. They're linear because they're on a line, right? Linear means that they're on a line, they're line-like. He's all good. Just exploded one of his pens. Good thing it was in your mouth. Linear pairs are angles that are on a line. They're linear on a line, and they're a pair because they go together, right? So 3 and 4 are a linear pair. There's a theorem called linear pair theorem. So let's use that by LPT. You're going to use this a lot. Linear pair theorem says that linear pairs are supplementary. That's it. They're 180. So I'm going to say by LPT, I know angle 4 and angle 3. I don't know what angle 3 is yet, so I'm just going to write it in black. Angle 3 and angle 4 are supplementary. Question, what does it mean to be supplementary again?
3 180.
So you're telling me 6 plus 4 is 180, and 3 plus 4 is 180. 6 and 4 180 because of the parallel postulate, right? 3 and 4 180 because they're on a line. Linear pair theorem, right? Linear pair, line, linear, pair, two of them. So if they both equal 180, what must be true about this and this?
They're equal.
They equal each other, right? If 1 and 3 equals 4, and 2 and 2 equals 4, you know 1 and 3 must equal 2 and 2, right? Well, numbers are hard. So we know this. We know that 6 and 4, therefore angle 6. Let's talk about the measure of it, right? Because we're talking about adding them up to 180. Angles don't add up to 180. That's like saying blue plus green is 180. What? Colors can't equal numbers. The measure of blue, well, that's a number. That's like 90 degrees or something, right? Measurements can add up to numbers because they're numbers. So the number that 6 is, however many degrees, plus the number of degrees 4 is, the measure of 4 plus the measure of 6, will equal the measure of 3 plus the measure of what?
What?
6 and 4 add together the same way that what and what adds together.
4, 3, and 4?
Yep. Because 6 and 4 are supplementary, they add up to 180. 3 and 4 are supplementary. So if they both equal 180, then they equal each other. You digging that? We cool with that?
And then the entirety of it.
That's a therefore symbol, by the way, a little triangle with 3 dots. When you bust that out, right, now you've gone like badass math. Like, I'm about to prove this theorem, therefore, right? You want to feel like a badass, that's the symbol you want to use.
Be scared of my dots.
Now, question. 5 equals 5, true or false?
Yes. True.
5 equals 5, I like it. 5 equals 5, true. We won't argue today. What if I subtract 3 from both? What do I get?
2 and 2.
I am not a crook. So 5 equals 5, 2 equals 2. Both are different statements, correct? But they are both true. 5 does equal 5, 2 does equal 2. So it looks like if I have something true, and I subtract the same amount from it, it'll still be true after I'm done. It'll be a different statement, but it'll still be true, yeah?
Yeah.
If I subtract the same amount from both these statements, angle 4 from both, it'll still be true. So when I do that, what will this say after I'm done?
3 equals 6.
3 and 6 are the same.
But I thought those were both the bigger angles of the bigger.
Measurements are equal because they're numbers. Ideas are congruent. So 6 and 3 are the same. And you're right, they are both the bigger angles. They're both the same measure. Does that make sense? Let me walk through this again. Let me back up and go over it again like a dead cat.
Okay,
What?
yeah, no, we're good. I'm good. They click.
These are supplementary. It's okay that you're good. I'm going to say it anyway. These are supplementary because parallel postulate, right? When they're parallel, they're sup. These are sup because of linear pair theorem, right? They're on a line. They must add up to 180. If these are sup and these are sup, this equals 180 and that equals 180. What's the middleman here? What do both have in common? What number do they both have in common? What angle?
4.
4, right? Take away what's common. What's left over must be the same.
Yeah.
Right?
Yeah.
Imagine angle 4 is, I don't know, 30 degrees. Because they're supplementary, what does angle 6 have to be?
What? Sorry.
It's okay. Math is hard.
No, can you say the question again? I zoned out.
Oh, no, you're good. You're good. If this was 30 degrees, what does angle 6 have to be? $150, because they have to add up to 180, right?
Yeah.
Okay, so if this is still 30 degrees, and this has to add up to 180, what does this have to be? 150, but yeah, it's okay, Numbers are hard. I mean that honestly. I know you know what you're saying, or you know what you mean, but you're not what you say. So if this is 30, that's 150. If this is 30 still, then that has to be 150 as well. See how they both end up being the same? It's because there's only one way to get from 30 to 180. You have to add 150. There's no other number you can add to it. It has to be the same number both times. That's what this is saying. They're 180, and they're 180. Green and blue make 180, so green and something have to make 180. Well, it's got to be blue again, right? That's all. How do I know that 5 is green? Someone explain that to me.
Because it's opposite of 4. They're called,
So you're seeing a pattern, and that's true. But much like kindergarten me, we have to ask, is that really the pattern, and how do we know? For instance, kindergarten me would say this. Teacher gets up and she says, okay, class, circle, square, circle, square. What's the pattern? What comes next? And the whole class says, circle, square, circle, square. Circle.
no, it's square circle.
Circle, square, circle, square. Next is circle, right?
Oh, yeah.
Your boy, you know what your boy would say? Triangle. And they thought I was obnoxious. And I was, but I was also right. What if that's not the full pattern? What if that's just a coincidence?
Yeah, the pattern could be longer.
You see what I'm saying? It could be longer before it repeats. Just because we see a pattern doesn't mean it is the pattern, right? We see a pattern here doesn't mean it is the pattern. How do we prove it's the pattern? How do we prove that this is green? We prove this is blue.
Because it's the same angle as 4.
How do we know that?
I'm going to keep going back to that pattern thing because it's,
And line up the side.
yeah,
That's true. So it looks like it's symmetrical.
yeah.
Looks like it. But didn't someone famous say,
Take it easy, it's just a drawing.
maybe it's not drawn perfectly and it's drawn symmetrical on accident? I need a good reason. What do you know about the relationship between 5 and 6?
They're 180.
What do you know about the relationship between 4 and 6?
They're 180.
Right? Because you know that from parallel postulate. So 5 and 6 relationship and 4 and 6 relationship is the same. In other words, they're equal to each other. 5 plus 6 equals 4 plus 6. What's common? The wrapper. But what else is common?
The middle axis.
6. 5 plus 6 equals 4 plus 6. Subtract 6 from both sides. 4 must equal 5. It's the same logic we used earlier. The reason I had you restate it is because obviously you didn't fully get it yet. I love asking the same question twice. So we're going to say, therefore, by the same dumb logic, the same thing we did earlier, right? Just with different numbers. You can say by similar logic. I say same dumb logic. By same dumb logic, cut to the chase. 4 and 5 are congruent. Remember how I said I love asking the same question twice? Well, I really love asking it a third time. How do you know 5 is green? Somebody tell me.
Because 6 is the middle axis between 6 is the common denominator between.
That's a metaphor that you're using to describe what's going on, but it's not telling me why it is. It's a metaphor. Explain logically why it must be green. We don't know it's green. And it's okay that you're doing that because it's going to take some getting used to explaining knowing what an explanation is and what it isn't. Okay? So don't be afraid. How do I know that 5 is green?
If 6 and 4 are the same.
6 and 4 are supplementary. Yep.
Yeah. And then if you move from the 4 to the 5.
Yep. So 5 and 6. What about them?
So, no, they're not supplementary. They're math terms are confusing.
4 and 6 are supplementary, right?
Yes.
What about 5 and 6?
They are not. Are they all supplementary?
They both add to 180, right? Why are 4 and 6 supplementary? Somebody tell me. Parallel postulate says they are, right? Why are 5 and 6 180? That's another way to say that they're 180, but why are they 180? Exactly. That's a reasoning, because they're a linear pair, right? And linear pairs are supplementary. So 4 and 6 are 180 because of the parallel postulate, right? If they're parallel, these are 180. 5 and 6 are 180 because they're a linear pair. So 4 and 6 and 5 and 6 are both supplementary. If they're both supplementary, what does that tell you about 4 and 6 and 5 and 6? They equal each other. 4 and 6 equals 5 and 6. Subtract the same from both sides. What's left over must be true. Again, let me show you with 3 and 4. These are supplementary because of they're parallel, right? These are supplementary because they're both on the same line. If they're both supplementary, then they both equal each other, right? Because they both equal 180. And if you take away the same from both sides, what's left over will still be true. We did the same dumb logic, but with 4 and 5. Supplementary, supplementary. Subtract what's left over will be the same. How do you feel about that, Jamie? I don't expect you guys to be 100% with that. How do you feel about that?
I'm like a solid 75.
75-ish? 75 is pretty good for first day. Yeah, 75? Okay. Okay. I'd go back and watch this video when you do this proof. And yeah, you could just literally copy stuff down, but don't do that. Try to take the chance to learn, because again, everything's made up and the points don't matter. Don't just copy it down. It's a waste of your time and mine. Try to understand it, right? Okay. Now we did our internal angles, right? And we proved basically that opposite internal angles, alternate interior angles, will be congruent. Always. Just if the lines are parallel, boom, boom, you know that for sure. How do you do that? Well, you prove it. Or you can use a theorem, right? We can construct a theorem out of this. It's always going to be true. We just proved it, right? So let's call it something. Shortcut, all of this just tells us that this and this are congruent. We'll call it alternate interior angles theorem. Alternate interior, alternate because they're on opposite sides, interior because they're on the inside. Alternate interior angles will always be congruent, won't they? If the lines are parallel. Ooh, good conjecture. So we can say by alternate interior angles theorem, AIA theorem, 3 and 6, 4 and 5. Now what if I said you weren't allowed to use alternate interior angles? I wanted you to prove it. Well, then you'd have to do this, right? Let's talk about the external angles. What do you know about 1, 2, 7, and 8?
They're the opposite matches.
Sure. How do you know?
Because they're not category there. I don't know how I want to say this, but
Let's take a break for a second. You guys are B-Day people, so you didn't have to meet with this Wednesday unless you did meet with me last week. We need to get that figured out. I can't do Fridays anymore like I'm going to do today, where I stay super late and help you guys out, because I have other things I have to do. Not fun things, but things I have to do, so I can't stay. So, like adult things. So on Wednesdays, when I give you the entire day to meet with me, I need you to utilize that, and if you can't, you got to tell me. That way I can put you on next Wednesday. But you're going to have to wait a week with a bad grade, okay? I don't care about the grades. If you don't care about the grade either, that makes 2 of us, right? But if you care about the grade, you need to talk to me. Right? So, and if your parents care, then maybe you care, right? So meet with me on Wednesday and let's get this stuff done. I'm going to stay late today, and if people want to show up, or I'll send out a link. I can do portfolio conference today until like 5 o'clock or so, or until people are no longer showing up. It's going to be first come, first serve, so it might be like I start it up and you guys all show up at the same time, and I say you first, you second, you third, and you have to watch for who leaves and who comes in. And I'm sorry for that, but that's just kind of the way it is if you miss Wednesday. But I need to meet with you guys, otherwise it can't give you a grade, right? Which is something you care about, I guess. So I'm doing it for you. I can't do that after this week. I can only do Wednesdays. So if you miss a Wednesday, you gotta wait to the next one. And you're sitting with a bad grade until. No, it's cool. Just get it done. Today I'll send out a link. So, now we've cleansed our brain of geometry for a second. 1, 2, 7, and 8. What do you know about angle 1?
the opposite of it.
Opposite of angle 4. Ooh, it's across from it. That's true. So we talked about this. This is something that you're going to have to do next week for a post, B-Day people. A-Day people already did. B-Day people, you had to do this. Oh, it's not on the board yet. All right. You guys remember Scissor Theorem, your words, not mine? Yeah. Otherwise known as vertical angles theorem. And it says that the vertical angles in an X will always be the same, always be congruent, right? Mm-hmm. Theorem, so we should be able to prove that. How do I know that the red angle is congruent to the black angle? Well, what we talked about last time, and what you're going to have to write a proof for, that look, what do I know about the red and the green angles? Give me a hint. What do I know about them?
On a line.
180 because they're on a line, right? So we'd say by linear pair theorem, which says that if lines, or if we have a linear pair, two angles on a line, right? We know that. We'll write it like this: measure of green plus measure of red equals 180, right? They're supplementary. Good one though. What do you know about black and green? How about relationships in here, guys? Same thing. By the same dumb logic, these are 180. Same reasoning, different things, right? Black and green. If they both equal 180, what's true about this and this? Yep. We call that a substitution. You see how this equals 180? So whenever I see a 180, I can take that 180 and switch it out for this stuff. See how I see a 180? Take this and put it there instead. They're interchangeable, right? So I'm going to take this. Whoops. I'm going to do it in the same order, even though it doesn't matter. Make it clearer. Whoops. They equal each other, right? How do I know this? Therefore, red is congruent to black.
Because they both have green in them.
You subtract both from the same side, right? You get a true statement afterwards. That's algebra. Whenever we just do algebra, just say therefore. Okay, I don't need to explain algebra. There's your proof. When you write this in your portfolio, don't try to do this in bold. What a nightmare. Angle symbols, congruency symbols. Oh, no. Write it on a piece of paper. You can use colors that way too. That's super useful for both you and me. Can you imagine learning this without color? Angle ABC is congruent to angle DBE because angle CBE is die.
Well, that's why people have.
I learned in black and white on a chalkboard. And by learned, I mean I didn't learn. Color changed my life. So we call this vertical angles theorem because the vertical angles, the top and the bottom, will be the same, right? The sides will be the same too, though. Right? Same logic. These two right here are 180. These two right here are 180. Subtract the middleman. These must be the same. So how do I know that 2 is the same as 3?
Because the kids are.
3 and 4 are linear pair, so they're 180, right? 2 and 4 are linear pair, so they're 180. 3 and 4, 2 and 4, subtract the middle. What's left over must be the same.
Yeah.
That's the proof of vertical angles theorem. So you could do that, or you could say by vertical angles theorem, 2 and 3 are the same. Yay, theorems. They're shortcuts, right? Now pretend you forgot what vertical angles theorem was, right before I showed you that. Pretend you, I know you didn't. You all knew it. You're sitting there, I know the answer. I just want to be I don't want to be a nerd. I know the answer. I just don't want to answer it, right? When I asked you, how do we know that's true, or how do we know this is true? You knew it. You just didn't want to say it. Pretend you didn't know it, okay? What could you do? Well, you could walk through the proof yourself, right? You could say, well, I know that this and this is 180, and I know that that and that's 180. Subtract the middle guy, you're going to get this. You could do this, right? And you'd get that. If you remember vertical angles theorem, great. You could just say vertical angles, they're the same. So how do I know 1 and 4 are the same? What's the quick way? Vertical angles, they're done. Right, we have an x. Vertical angles are going to be the same. The hard way, well, I know 3 and 4 are 180, and I know 1 and 4, or 1 and 3 are 180. Subtract the middle guy. What's left over is the same. You could do this, right? All about explaining. So I know 1 and 4 and 2 and 3 by vertical angles are the same. So I'm going to write that. By vertical angles theorem, and if I tell you have to prove vertical angles theorem again, you could do the 180 thing, right? I know 1 and 4 are the same. And I know 2 and 3 the same. But that's not all I know. What about 7 and 8? Mm-hmm.
Linear pair.
7 and 8 are a linear pair. They're 180. What about 6 and 8? Yep. Oh, sorry. 6 and 8. Yep, they're also linear pairs, so they're sup. Cut out the middle guy, 6 and 7 are the same. Or the shortcut, vertical angles, boop, done. What about 5 and 8?
The middle man would probably be 6.
Yeah, 5 and 6, 6 and 8, 6 middleman, 5 and 8 the same, or shortcut, vertical angles, right? So I know 5 and 8, 6 and 7. Let me add on to here, because they're all the same. And then 6 and 7 over here I can write out nicely. We got all that information just because these are parallel. That's a lot of congruent angles. A lot of mixing and matching. Turns out, alternate interior are always the same, right? And according to parallel postulate, same side interior are supplementary. There's always a where are your gods now problem. Here's the where are your gods now. I want you to take a little like break while I draw it out because you need the break. All right. That's what we had last time, yeah? Ooh, they're still on break. Never mind. I'll give you more time.
Wait, no, you're...
No, it's fair. I'm not mad. I'll give you more time. I screwed up my drawing anyway. The one sad thing about switching to Google Meets is that I won't be able to use the soundboard as much. Oh, those are good.
Reminds me of pretzel.
Waffle fries.
Yes, thank you.
Words are hard.
I haven't had a good waffle fry in so long. Do you know where you can get good waffle fries around here?
Nope. Where are your gods now?
They don't exist.
I'm going to tell you that L and M are parallel. So I'm going to use these little symbols to say that. And I'm also going to tell you that N and P are parallel. If I only use one little triangle, though, it looks like I'm saying that P and L could be parallel as well, which ain't it, Chief, right? So I'm going to use double triangles to say that those go together. So what I'm telling you is that L is parallel to M, and N is parallel to P, and not crisscross, right?
Vertical angle here.
Something like that. What do you know about these angles? Let me zoom in. What do you know? We've got two sets of parallel lines. What do you know? Well, we know 1 and 4 will be the same, right? 2 and 3 will be the same. But do we know that... Let's do that. Let's do that. So 1 and 4 are the same by vertical, right? And we know 2 and 3 are the same by vertical as well. So I'll write that down.
Shouldn't that mean that are these drawn parallel on purpose, or they're drawn parallel on accident?
Nope, they're parallel. I marked them as such. You can trust markings.
Okay, then shouldn't each corner be vertical angle theory true?
Hold on one
True
second.
vertical angle theory?
We know that by that. We have vertical angles theorem. So what are you talking about, Demery?
Shouldn't each corner marking, each where each
Give me numbers. So
9 and 10, 11 and 12, they should all be equal via vertical.
yeah, so 9 and 12 and 11 and 10 would be vertical as well. But here's the thing. If I do that, does that mean that they're blue and green? I'd have to do like pink here and then like purple there because they could be different than this, right?
Yeah.
However, I'm going to tell you right now that there's actually a connection between some of these. So I'm not going to mark that down yet because I'd hate to mark them pink and purple and then find out later they're actually blue and green, right? These things are permanent.
Well, it could technically be because. No, wait, yeah.
We'll think about it. If I cover this up, this is a problem you're familiar with. What we just did, right? 2 parallel lines, 1 transversal. What do you know about parallel lines? What's the fifth postulate say? Because we got all the angles here, but we need some connection down here, right? What does the fifth postulate say? The parallel postulate. If the lines are parallel, what do you know? Which angles do you know about, and what do you know about them?
You know, the middle angle.
The middle two, 4 and 6, are what? Not sus, but no, linear pairs when they're on the same line together, right?
No,
like this.
I can't.
Not sus, but what?
Sup.
Sup. Supplementary.
I heard sus and I thought you said sus.
I know, I know. So they're supplementary. That's great, but I don't know that it's green yet. Not necessarily. So I know that 4 and 6 are supplementary. I know 4 is blue because I said it was earlier, right? And then let's leave 6 black for now. We're going to prove that he's green. 4 and 6 are sup by the parallel postulate, or the fifth postulate. So that means they had a 180. How do I know green, or 6 is green? I know they had to 180, but how do I know it's the same as 3? I know they're 180, but how do I know that 6 and 3 are the same?
Because 4 is the middle one.
Yep. So talk me through it, because that's not an explanation. That's a metaphor.
6 and 4 equal 180.
Mm-hmm.
Then 4 and 3 should be 180 because they are linear pairs.
Hell yeah.
And then since 4 is the common in both pairs, 3 and 6 should be equal if you take out 4. Thank you.
Hell yeah. So check it out. 6 and 4 are sup. We already said that. Parallel postulate. 3 and 4 are sup because what reason? Can you give it to me again, Demery? 3 and 4 are sup because they are
3 and 4 are sup because they are linear pairs.
by linear pair theorem. Yep. Mm-hmm. And linear pair theorem says they're supplementary. So by LPT, 3 and 4 are sup. Good. And if they're both supplementary, what does that mean?
That 3, no, wait, hold on. That 3 and 6 are.
Yeah, that's eventually what we'll get to, right? Because 4 and 6 plus 3 and 4 is going to be the same thing as 3 and 4.
Oh, actually, just that, sorry.
Yeah, no, it's cool. It's cool. Totally cool. Now we're here. And then we subtract the same from both sides, and it should still be true, right? That's the idea. If you have true before, and we know it's true because we were logical, right? Then if we subtract the same afterwards, it'll still be true, which means 6 and 3 must be the same thing. And now I can write them both in green. I like Sharpies. You all like Sharpies?
Yeah.
Spell Sharpie.
Whoa.
The smell of Sharpie makes me sick.
They have like facilities where you can get help for that.
Only one hard Sharpie. Sharpie!
They'll wean you off that. All right, so I would encourage you guys to get Sharpies or some kind of pens. These are really great too. The reason I don't use these on stream is because they're really thin. But normally I use them all the time for math. It changed my life. I became sucky at, I went from sucky at math to good at math. Get yourself a binder if you can afford one, a 1-inch binder. If you can't, find somebody you can and steal it from them. Or I'll buy you some, right? But try to get that for next week so I can fill it with graph paper so you can start doing some of this, okay?
I'll commit
burglary.
You know what also smells good? Gasoline.
Oh, my mom also smells
Yikes!
gasoline.
Yikes! Did you know some people think the decrease in crime over time, because we actually have less crime now than we did 20 years ago, believe it or not.
Really?
Yes. A decrease in crime they think is because they stopped putting lead in gasoline because people smell it, and lead would get more violent.
Really?
Yeah. Like mold and gas.
I like mold. I can't stand smoke gasoline.
Here, see you later, man. Ugh. See you guys later. Have a great weekend. Get that stuff done. See you today. Oh, it's fourth hour. Wait, no, that was fourth hour. That was my fourth hour class. I had third hour. I was given. Very strong third hour vibes. Welcome, Bailey. Today we talked about the most important postulate of all 5 of Euclid's postulates, the fifth postulate. The fifth postulate, Bailey. Your favorite postulate, of course. The postulate that says, and again, postulate leap of faith, right? Because we have to build math upon leaps of faith. We want as few as possible. Euclid, for the longest time, refused to have a fifth postulate. Like, God damn it, I can prove it. I know I can. And then eventually gave up. Turns out, if it weren't true, it leads to what's called non-Euclidean geometry, which is like space-time geometry, how space is curved. But, yeah. So, not the fifth postulate is the parallel postulate, or PP for short. It says that if 2 lines are parallel, or no, actually it's the other way around. He phrases it backwards. If I have 2 lines and a transversal crossing them, and the same side interior angles are supplementary, you can imagine them both being 90, right, straight up, then that means that these lines are parallel. So if green, red are sup, ampersand, then L parallel M. And this actually goes both ways. So if they're parallel, these will automatically be supplementary. And from that, you get alternate angles on the fixed. If this were not true, because again, it's hard to prove that these lines never intersect because they come forever. Euclid for the longest time wanted to prove it because we only wanted 4 postulates. Having a geometry that's based on only 4 leaps of faith instead of 5 things you just got to trust me on is a lot better, right? But he couldn't do it. He eventually wrote like 3/4 of his book and was like, okay, fine, postulate. And it turns out, as mathematicians, we have an option. We can either say trust it or don't, which is more interesting. And Euclid came to the conclusion I'm going to have to trust it because while it is more interesting not to, if these were to intersect, it leads to a lot of triangles no longer add up to 180 degrees. And all kinds of stuff. All lines intersect. Non-Euclidean geometry is born, which is where you get hyperbolic space, or like a triangle drawn on here. So this triangle right here, if you were to measure the angles, actually wouldn't be 180. Because we're no longer on a flat surface. If I were to take this curved surface, like rip off the map and lay it flat, one wouldn't lay it flat for and curved. And straight lines on here would be curved. So you, if I lay it flat, and vice versa. What's interesting is that, fast forward 100 years later, Einstein says it turns out Euclidean geometry, flat surface geometry, isn't really how the world works. The world is round. Which, you know, fine, right? What's more interesting is that space-time is curved. So, gravity, right? You don't really know what it is, there's a theory behind it, right? Einstein says this. Imagine a trampoline. Imagine the whole floor is a trampoline. And in, over here, Parker, with his sick boots, okay? They're like 200 pounds and like dragging down that trampoline. I'm a golf ball. What's going to happen? Dragging down the trampoline. Where am I going to go? I'm going to go toward like a planet. Okay. Einstein says the fabric of space-time is the fabric of a trampoline. And heavier objects pull that down more. They bend in space. So it turns out, going in a straight line in space, you're actually curving, and curving in space, you're actually going in a straight line. Gravity distorts space-time, mass does. So it turns out almost more accurate to describe the universe that these do intersect. So, yeah, so when we think of a triangle, right, it's really imaginary. It really doesn't exist in real life. It's just very close, but as soon as you get into really big things or really, really small microscopic things, you realize that's not really what's going on. Question is, which is more true? Universal theory of everything, right? How do we connect that? How do the big stuff and the small stuff exist in the same universe as us, but obey, you know, they have to obey the same rules, right? Theory. But yet they don't. So Euclid's like, that would just be too crazy. Fast forward 100 years later, you know, hundreds of years later, and like, well, actually, yo, you what? I got you. Eat man. You want black pen or you want colored pen? No, don't get up. Giandrolima, middle of class, he's online. School's canceled because of COVID. But, of course, instant panic, everybody. What? No school? Oh my god. Here we are. Dumb kids. Oh, bars and restaurants definitely are. I don't know about school. See, Bailey, you're thinking too much about it. You're thinking too much. That's your problem, okay?